No comet this far out should be glowing. That's the first wrong note. Comets are supposed to wake up near the sun when water ice warms, vents open, and dust sails outward under pressure and light. Yet BBC 2014 UN 271 Bernardinelli-Bernstein is already active in the outer solar system, far beyond the realm where water drives the show. The activation isn't a rumour, it's radio. ALMA has detected carbon monoxide in emission and observed its outgassing geometry change over days, a low-temperature engine running where intuition says it shouldn't. Start with what we can measure. In March 2024, at a heliocentric distance of 16.6 AU, ALMA detected the COJ equals 2,1 line at 230 GHz and a compact thermal continuum consistent with a large nucleus and a faint dust coma. 2 epochs separated by 9 days revealed multiple narrow jets that evolved between observations, structure, not noise. The preprint lays out the integrated flux maps, CO production rates, and stringent upper limits for other species. The accepted AppJL version confirms those detections and times. In plain language, the coma is molecularly alive, and the pattern of activity is changing while BB is still well past Saturn's orbit. Why does that feel uncanny? Because most of us learned the water rule. Sublimation of H2O turns on inside roughly 3 AU. Carbon monoxide is different. It volatilizes at far lower temperatures and can drive distant activity in extremely cold comets. BB's CO line is precisely the signature you'd expect if a large, volatile-rich body is slowly heating from deep cold and venting through discrete active areas. The emotional tone here is unease, not panic. The system is acting lawfully, but the law it's following isn't the one casual comet law taught us. This isn't a Hollywood glow, it's a physics glow, and its early scale matters. Hubble's 2022 analysis separated the nucleus from its surrounding coma and set the size near 85 miles to 137 kilometers across the largest comet nucleus measured with confidence. A nucleus on the 100-kilometer scale changes both the energy budget and the observing strategy. Signals get cleaner, thermal emission is detectable at greater distances, and the aerodynamic balance between gas thrust and gravitational self-binding plays out differently than in a 210 kilometers typical comet. When you combine very large with already active, you get a target where fine-grained questions, dust size distribution, jet collimation, spin axis, geometry become answerable years before perihelion. The timeline is also unsettling in a productive way. BB didn't burst onto the scene as a bright apparition. It was mined out of the Dark Energy Surveys archive. DES pipelines flagged a slow, coherent mover in years of wide-field data, and NOIRL announced the discovery publicly in June 2021. That origin story matters because it previews how well catch the next object. Algorithms first, telescopes second, then a multi-year relay across wavelengths. BB is both a science target and a rehearsal for survey-era cometology. It forces us to ask, how do we schedule and share radio, optical, and infrared time when the object wakes up before most of our old rules say it should? Where does this go? Not toward a dramatic dive. The orbital solution places perihelion in late January 2031 at roughly 10.95 AU, still outside Saturn's orbit. That distance is safe for Earth and an opportunity for science. It gives us years of controlled cadence to bracket phase angles, build a clean light curve, and watch whether tiny code-driven thrusts integrate into a measurable, non-gravitational term in the orbit fit. The A and A orbital work and public elements agree. The date and distance are pinned well enough to plan around, and the inclination is steep, an Oort Cloud traveller in every sense. Already active can mean several specific, testable things, and BB lets us test them. First, line physics. The COJ equals 2,1 brightness, line width, and spatial morphology constrain production rates and outflow velocities. If those evolve with heliocentric distance and subsolar latitude on the nucleus, we can invert for active area distribution and rotational modulation. Second, continuum. A compact thermal signal at millimeter wavelengths constrains effective size and albedo when combined with optical photometry. Third, cross-species limits. non-detections, for example, H2CO, tell us which chemical pathways are quiet, while CO dominates. All three knobs, line strength, continuum, and limits, are available now, not someday, because the coma has switched on early. Unease also comes from what early activity implies for the surface and interior. If CO is escaping through localized vents, are those vents primordial pores, impact fractures, or stress-induced cracks from slow warming? If jets are narrow and persistent, do they map to fixed topography on a large, possibly low rotation rate body? Conversely, if morphology drifts over weeks to months, does that argue for seasonal illumination changes on a tilted spin axis? Early activation gives us a long runway to separate those hypotheses with repeatable geometry rather than one frantic season near the Sunday. The ALMA epochs already show geometry changing on human timescales. The question now is whether the size-distance activity triad reframes outreach too. When you tell someone a comet is glowing beyond Saturn, the honest follow-up is, it's CO, not water. That nuance keeps awe aligned with accuracy. It also helps inoculate against false comparisons. You may see claims that BB is X times more massive than some interstellar comet. Many such ratios are impossible to verify because the comparison object's mass is poorly constrained or unknown. We will not lean on numbers that can't be independently checked. We will keep to what's measured and citable: nucleus size, Hubble, molecular activity, and jet structure. 1. Glowing here means CO line emission and a compact thermal continuum at 16. 6 AU, molecular, not water-dominated. 2. The nucleus is enormous, to 85 miles across by Hubble's coma subtraction analysis, which strengthens signals and stretches the observation window. 3. The orbit gives us years. Perihelion is late January 2031 at 10.95 AU, with enough certainty to schedule campaigns rather than scramble. 4. The jet field evolves across days, implying structured, rotating, or seasonally shifting activity we can map, not just infer. From this frame, the next parts become straightforward: motion and tiny thrusts, brightness versus geometry. It's not a comet, it's a monument. Start with a number that forces a recalibration of scale, about 85 miles across. That is the nucleus diameter Hubble extracted for C. 2014, UN 271, Bernardinelli-Bernstein, BB. After subtracting the coma and modelling reflectivity roughly 137 kilometers, the largest comet nucleus ever measured with confidence. The same analysis framed the mass at to 500 trillion tons, on the order of 100,000 times a typical inner system comet's mass. These aren't banner words. They're the load-bearing facts that everything else rests on. Most of us learn to picture comets as town-sized snowballs. BB is something else. Hubble emphasized that its nucleus is about 50 times larger than most known comet cores. A leap that doesn't just look impressive, it changes what we can read from the signal. A 100-kilometer class body emits more thermal radiation at great distances, can sustain activity without immediately compromising its structure, and gives observers cleaner leverage to separate dust from gas in the coma. When there is more signal, earlier, with lower noise, the questions you can ask become sharper and the answers more durable. Put that scale in a context your intuition recognizes. Ceres, a dwarf planet, spans to 940 kilometers, an order of magnitude larger than BB. But finally, a reference that lives comfortably in your head. BB is not a dwarf planet, nowhere near hydrostatic equilibrium, but calling it town-sized is comically inadequate. If Ceres is the capital, BB is the skyscraper district. Massive, coherent, and tall enough to redraw the skyline of any mental model that still files comets under pebbles. Now add distance. BB's closest approach to the Sun comes around late January 2031 at roughly 10.95 astronomical units, still beyond Saturn's orbit. That geometry is safe for Earth and an opportunity for science. It turns urgency into cadence, years to book optical, infrared, and radio time, seasons to build phase-angle light curves, room to test whether tiny thrusts from venting integrate into measurable non-gravitational terms in the orbital fit. You can verify both the perihelion timing and distance in public orbital solutions. The point is not to memorize the date, but to understand what far buys us. Method. The scale becomes at stake the moment you think about energy and structure. A nucleus, this large, absorbs heat slowly and conducts it through shallow layers without catastrophic failure. That means early activation can persist without the body disintegrating under thermal stress. It also means small jet thrusts, imperceptible in an instant, can add up over months into orbital nudges we can actually fit. With a 5-kilometer nucleus, such terms blur into noise. With a 100-kilometer nucleus, they can survive the averaging and stand out as physics instead of artifacts. The activation itself is not a rumor but a spectrum. In March 2024, at 16.6 AU from the Sun, ALMA detected the carbon monoxide J equals 2, one line at 230 GHz and a compact millimeter continuum consistent with a huge nucleus plus a faint dust coma. 2 epochs, 9 days apart, showed multiple narrow jets that evolved between observations, structure, not noise. The preprint lays out integrated flux maps, production rates, and limits on other species, and subsequent summaries have reinforced the core result. BB is molecularly active in deep cold, exactly the regime where CO, not water, should lead. A monument that breathes quietly, lawfully long before the warm inner system comes into play. That one line, CO, J equals 2, one does a lot of work. It constrains production rates and outflow speeds. When tracked over heliocentric distance and subsolar latitude, it lets us invert for active area distribution and rotational modulation. Combine line measurements with the continuum and with optical photometry, and you can bracket effective size and albedo while also passing the dust size distribution from the phase angle light curve. Big isn't a flex here. It's a method that turns is anything there into how is it arranged and why. Discovery context matters because it previews the pipeline we will need again. BB did not blaze into human awareness by being obvious. It was mined out of the Dark Energy Survey's archive after 6 years, an algorithmic success story. NOAA Labs' June 2021 announcement is the pivot from surprise to process. Archival detection orbit solution, multi-wavelength relay, years long. BB is both a target and a rehearsal for survey-era cometology, where discovery, confirmation, and characterization are distributed systems, and time is a resource you manage across observatories. Comparisons are inevitable. Sloppy comparisons are optional. You'll hear 10,000 times more massive than X, often with an interstellar visitor as the foil. Resist that shorthand unless both sides of the ratio are real numbers with citations. For 3I, Atlas, for example, nucleus size and mass are not yet securely established in peer-reviewed literature. Any object-to-object mass ratio would therefore be speculation. What you can say, cleanly, is that BB's to 137 kilometers nucleus dwarfs sub-kilometer interstellar nuclei, like 2I, Borisov's constraint set, and it certainly dwarfs anything in the meter to hundreds of meters reconstructions of 1I, Oumuamua. The message is scalable without the guesswork. We will update if and when 3I, Atlas, gets a robust size, mass determination. A monument also buys you time to watch patterns settle. If jets are tied to fixed topography, repeatable position angles should phase lock to the rotation period. If outbursts migrate, that argues for seasonal illumination or evolving fracture networks. Because BB stays far, we can test both hypotheses without the glare and chaos of near-sun water domination. And because the nucleus is so large, even modest dust production won't erase the core over a single apparition. That gives you a long-form laboratory for dust mechanics, grain sizes, ejection velocities, radiation pressure, sorting into fans and filaments. Each observing season becomes a chapter, not a footnote. Scale clarifies outreach as well as analysis. When you tell the public a comet is glowing beyond Saturn, the honest follow-up is that it's CO, not water. That simple sentence inoculates against the idea that something mystical is happening. It also makes the ore safer, wonder without myth. Skyscraper of ice is the metaphor, but the guardrails are measurements, the Hubble nucleus size and mass framing, the orbital geometry that keeps the encounter unhurried, the ALMA line that says, in a narrow band, I'm alive. Even basics like brightness turn into tools at this scale. A larger nucleus means the continuum is visible earlier, and the coma's handwriting in color slopes and phase dependence becomes legible at lower noise. That's how you separate coarse grains that hang near the body from fine grains driven into broad fans. That's how you see whether thermal emission tracks subsolar latitude cleanly or lags in a way that hints at stratified layers. The same size that inspires the headline equips the experiment. None of this asks you to suspend skepticism. Every claim we're leaning on is checkable. The nucleus size and mass framing, Hubble's the 12th of April 2022, release and associated materials, the perihelion date and distance, peer-reviewed orbital work, and public elements that agree to useful precision, the CO detection at 16.6 AU with evolving jets, observing logs and maps from ALMA's March 8 and 17, 2024 epochs. If a statement can't be traced, it doesn't belong here. So when we call BB a skyscraper of ice, we mean it precisely in 3 registers. Absolute, to 137 kilometers wide, record-setting for a comet nucleus, and heavy enough to keep its shape while the sun works on it slowly. Relative, towering over the interstellar comets we've met so far, and over the small, short-lived nuclei that dominate catalogues. Practical, bright, and structured enough, early enough, at safe distances, to let us test hypotheses instead of trading metaphors. Big is not bravado. Big is a way to see. Carry that architecture forward, because the next questions depend on it. Size tells you why the thermal continuum is present early. CO at 16.6 AU tells you why chemistry leads before water. Perihelion, beyond Saturn, tells you why this can be a careful, multi-season investigation rather than a scramble. In Part 3, we'll move from scale to motion and brightness, how tiny thrusts reveal the engine, and how geometry writes itself into the light curve. For now, hold the monument in your mind not as spectacle, but as structure, and notice how much more stable the story becomes when awe stands on numbers. It's not circling with the planets, it's diving through them. Planets keep their traffic neat. They move in a thin, shared sheet called the ecliptic. Most short-period comets, tugged and recycled by the giant planets, more or less respect that plane. BB doesn't. Its path knifes almost straight through the planetary disk, tilted about 95 degrees so steep it's essentially perpendicular and slightly retrograde. That geometry is not a rounding error. It's the headline. The orbit solution pins a perihelion around late January 2031 at roughly 10.95 AU. But the shock is the tilt, an inclination near 95.5 degrees. You can verify both numbers in the public elements. Why does a single angle feel so disorienting? Because orbit equals plane is one of the few instincts space gives us for free. The ecliptic isn't just a classroom diagram. It's where our telescopes, surveys, and expectations spend their attention. We assume arrivals will skim that surface. BB ignores the surface and comes in like a spear. At 95 degrees, the motion is not merely slanted, it's retrograde against the usual direction of planetary travel and almost orthogonal to the solar system's primary lane. That's the signature of an object that hasn't been domesticated by the planets. It's an Oort Cloud arrival, not a homegrown commuter. Set the basics. Long-period Oort Cloud comets do not share a single plane. Their inclinations are nearly isotropic, with many orbits strongly tilted or outright retrograde. That distribution follows from how they're fed inward, gentle but persistent torques from the galaxy and random shoves from passing stars nudge some far-flung bodies toward the sun on whichever planes those nudges produce. In other words, weird inclinations are normal for this population. The ecliptic is the exception, not the rule. Reviews on Oort Cloud dynamics have been saying this for decades, and modern treatments, numerical and analytic, arrive at the same conclusion. BB's 95 degrees is exactly the kind of wrong that means textbook right for an Oort arrival. But the consequence is still jarring when you plan observations. A near-perpendicular, slightly retrograde orbit slices quickly through the planetary plane, so the times when BB shares sky neighborhoods with planets are brief and geometry sensitive. That reduces close encounter odds. Its Jupiter-moid is to 6 AU, but it also means the object samples a wide range of solar latitudes as seen from Earth. For survey cadence, that forces adjustments. You aren't sweeping along the ecliptic anymore. You're scheduling a moving target that spends much of its time off the usual highways. The upside is that unusual phase angles become available, and those can be gold for reading dust, scattering, and coma structure without the usual crowding. The inclination also telegraphs a clean dynamic history. Objects that have spent time inside the planetary system tend to be pruned into families. Jupiter family comets, Halley type, their inclinations moderated by repeated encounters. BB's 95 degrees says the planets haven't done much sculpting yet. In the language of dynamical diagnostics, its Tisserand parameter with respect to Jupiter is strongly non-Jovian, consistent with a long-period Oort Cloud origin. That matters because it makes interpretation cleaner. When we see non-gravitational nudges from outgassing in the orbit fit, we can read them against a background that isn't already tangled by a long history of planetary kicks. What put BB on this plane? The most honest answer is a combination of weak, distant hands, vertical, galactic tides. The galaxy pulling up and down on the solar system are efficient at changing perihelia of very distant bodies. Passing stars add stochastic kicks. Together they refill the inner system flux with comets on all possible orientations. Simulations that inject millions of synthetic Oort Cloud comets under galaxy plus stars reproduce the broad, near-isotropic inclination spread, including steep, retrograde cases like BB. No single star needs to have thrown BB at us. The cloud's slow breathing under tides and encounters is enough. That wrong-way geometry reframes the science plan in three practical ways. First, it decouples our measurements from the ecliptic's usual glare and crowding. With BB spending so much time off the plane, we can pursue deep, long integrations at phase angles that are awkward for ecliptic huggers. If you care about the comas, handwriting polarization changes, color slopes, phase-dependent brightness, this is a feature, not a bug. The orbit hands us a set of geometries where competing backgrounds are lower and scattering physics is easier to read. You saw in part 1 why we value long, clean phase coverage. The orbit gives us the chance to get it. Second, the steep tilt reduces the role of planetary perturbations during this passage. Jupiter will not dominate the narrative. No hair-trigger encounter geometries are waiting to eject or shred the trajectory. That stability helps when we chase tiny non-gravitational terms. We can ask a precise question. Do co-driven jets produce a persistent A1, A2 in the orbit solution, without watching the answer drowned by a random planetary kick? The near-perpendicular approach, paradoxically, gives us a calmer laboratory. Third, the tilt complicates some logistics in exchange for better leverage elsewhere. Radio arrays and space telescopes, scheduled for ecliptic targets, need flexible windows. Ground networks must plan for high declination tracks at odd hours, but because perihelion sits at to 10.95 AU, we have years to rehearse the handoffs. The geometry is wrong relative to habit, not relative to physics. That difference, habit versus law, is the thread we pull through this whole part. Let's put numbers back on the table so the disorientation stays honest. The orbital elements give inclination is approximately equal to 95.466 degrees inbound and is approximately equal to 95.46 degrees outbound. Perihelion distance Q is approximately equal to 10.95 AU. Next, perihelion is approximately equal to 23 January 2031. Jupiter moid is approximately equal to 6.1 AU. None of those are rounded myths. They're the live elements maintained in public references and kept consistent across ephemeris services. Read them yourself, then look again at a diagram of the ecliptic. What you'll feel is the right kind of off, not a contradiction, a correction to a mental shortcut. There's a communications trap here, and well avoid it. Calling BB's orbit wrong can imply anomalous or unnatural. It isn't. For Oort Cloud comets, steep and retrograde orbits are ordinary. The unease comes from our bias. We live inside the planetary plane and design our surveys around it, so orthogonal visitors feel like gate crashers. Dynamics says otherwise. The Oort Cloud is a spherical reservoir. Its emissaries arrive from everywhere. The ecliptic is our parochial slice of the sky, not the universe's default. How does this tie back to the chemistry and size you've already met? The orbit controls the viewing geometry. The size controls the signal. The chemistry controls what the signal means. A 137 km class nucleus gives us a measurable continuum. CO, seen at 16.6 AU, tells us the engine is on in the cold. A 95 degrees inclination sets the stage to measure both without the usual ecliptic traffic in the background. The three are not separate stories, they interlock plane, bulk, and breadth. In the next part, we turn that geometry into practice: brightness versus angle and time. If the comet's dust is coarse, the light curve will say so. If jets are collimated along a rotating axis, polarization and morphology will betray the spin. If tiny thrusts from venting integrate over months, the orbit fit will grow a measurable non-gravitational term. The wrong orbit isn't an oddity you apologize for. It's the scaffolding for a cleaner experiment. The discomfort it triggers is useful. It forces us to leave the comfort of the plane and meet the comet on its terms, nearly perpendicular, slightly retrograde, and, for once, exactly where the textbook said an Oort messenger should be, if it's been asleep for 4 billion years. What just touched it? Start with the only honest frame. Big comets from the Oort Cloud do not usually decide to visit. They are nudged. The two steady hands are the galaxy itself and passing stars. The galactic tide, the large-scale gravitational field of the Milky Way, very slowly talks the distant reservoir of the Oort Cloud, changing perihelia until a few bodies leak sunward. Numerical work since the 1,980 seconds, refined many times since, shows that this tide is the dominant, long-term injector of long-period comets. Individual stars add punctuations and scatter around that background flow. That's the orthodox picture, and it matters because it says waking up is a process, not a singular miracle. Now make it concrete. We have seen a star pass through the Oort Cloud in humanly recent geological time. About 70,000–80,000 years ago, Scholz star, a dim red dwarf with a brown dwarf companion, passed within roughly 0.3–0.5 parsec of the Sun, grazing the outer Oort Cloud. Analyses of its trajectory, using proper motions and radial velocity, place the closest approach around 50–70,000 AU. The encounter was likely too weak and too recent to have produced an immediate comet shower at Earth. Inner arrivals would take 1–2 Mir to fall in, but it is a proof of principle. Stars do thread the cloud, and they do it often enough to matter. Then zoom forward into 1.31. 4 million years, Gliese 710, a K-dwarf currently to 63 light-years away, will sweep far closer than Scholz star, with a predicted perihelion around 10–14,000 AU, 0.05, 0.07 PC. That will be a strong perturbation of the outer Oort Cloud, and modern orbit reconstructions using Gaia astrometry have converged on the timing and distance. Again, this is not a scare line for tonight. It is a reality check on the mechanism. Weak, frequent tides, plus occasional near-miss stars, refill the long-period comet flux that we observe. So what, specifically, could have woken BB? The safest answer is the same quiet machinery, a combination of galactic tide and one or more weak stellar tugs sometime in the last few million to tens of millions of years. Simulations that evolve synthetic Oort Cloud comets under both ingredients reproduce the observed near-isotropic inclination distribution and feed a steady trickle of high-inclination and retrograde objects like BB into the planetary region. That is, nothing special has to happen to explain a 95 degrees inclined, distantly active giant arriving now. The slow breathing of the cloud under tide plus stars is enough. But our unease isn't only dynamic, it's chemical. BB is already on at 16.6 AU. ALMA has directly detected the COJ=21 line from its coma and watched narrow jets change over a 9-day baseline in March 2024. That's a low-temperature engine consistent with a large supply of very volatile ices and localized vents activity that can switch on far beyond the waterline. In other words, whatever nudged the orbit merely delivered the body into a solar heating regime where its most volatile inventory can work. The wake-up you're seeing is physics, not theatrics. Let's test hypotheses against what we can actually check. Hypothesis 1. A stellar flyby did it. This is plausible in principle, but for BB, we have no named culprit. Known recent or upcoming perturbers bracket the concept Scholz past graze and Gliese 710 seconds future plunge. But tying BB to a specific star would require backward integrating BB's orbit through the poorly constrained stochastic, history of the cloud, and cross-matching with stellar encounter catalogues with uncertainties of their own. There is no peer-reviewed paper that identifies a particular flyby as the trigger for BB. I cannot confirm this. What we can say, stellar passages of the Oort Cloud do occur on Mert and Mer timescales, and they add to the tide's background push. Hypothesis 2. The galactic tide did it. Slowly. This is not only plausible, it's expected. Classic analyses and modern N-body work agree that the vertical component of the galactic tide is efficient at lowering perihelia of very distant comets, seeding the observable flux without the need for a particular stellar kick. For a very large body like BB, with substantial volatile inventory, once perihelion moved inward enough, CO could start venting long before water, exactly what ALMA sees. This is the null hypothesis. The tide nudged the orbit. The sun's distant heat woke the chemistry. Hypothesis 3. A short cycle did it, for example 14,400-year periodicity. Periodic shower claims crop up whenever humans search for patterns in crater histories and comet arrival times. Comprehensive reviews of Oort cloud dynamics and long-period comet fluxes do not establish a robust 14.4-year cycle in injections. The dominant drivers act on far longer timescales, mere and produce stochastic, not clock-like, delivery. There is no peer-reviewed support for a 14,400-year injection cycle tied to tides or known stellar passages. I cannot confirm this. Now follow the logic chain from nudge to glow. A small reduction in perihelion distance, accrued over many orbits under tide, plus stellar noise, moves an object from thermally inert into co-sensitive. In a 100-kilometer class nucleus, that switch can flip distantly and persist gently. Vents open where subsurface CO reaches pathways to vacuum. Collimated jets appear. Rotation modulates them, and the coma's line emission becomes detectable long before the inner system. That's precisely the sequence ALMA's 2 March 2024 maps hint at. A CO-bright coma with multiple evolving jets, plus a compact continuum consistent with a very large nucleus and tentative dust. The anxiety you feel is our mental model catching up. The inner system water story is not wrong, it's incomplete. Does BB's unusual size change the trigger story? Indirectly, yes. A larger body has more phase space to retain volatiles over gigayears and to conduct and store heat without catastrophic failure. When nudged inward, it can sustain low-temperature activity over long arcs of its orbit. That stretches our observation window and raises the odds that we catch the wake-up in progress, exactly what happened. But size doesn't pick the trigger. It amplifies the consequence. The tide still provides the lever. The star, if any, adds a shove. The nucleus supplies the fuel and the plumbing. Could there be a third agent? Dense interstellar clouds, spiral arm crossings, or collective effects from multiple weak encounters have all been discussed as higher-order contributors. In practice, their signatures fold into the same language of perihelion evolution. They alter the rate and spectrum of injections, but on the timescales that matter for one object's arrival, they look like modulation of the tide plus star's baseline. If future Gaia releases revise the roster of past close encounters, well, revisit whether a named star fits the chronology. Until then, galactic tide with possible stellar seasoning remains the least surprising answer that fits the data. Where does this leave the story? With a mechanism we can monitor instead of a mystery we must mythologize. The question, what touched it, becomes 3 operational tasks. Map the comas.co kinematics across seasons to see whether jet position angles repeat rotation-locked vents, or migrate seasonal illumination, evolving fractures. Track low-level non-gravitational terms in the orbit solution. If jets impart persistent thrust along fixed axes, small, A1, A2 terms should integrate over months into a measurable signal. Keep a rolling ledger of stellar encounters from Gaia-era catalogues and test whether any statistically credible past flyby aligns with plausible injection times for a body now at Q is approximately equal to 10.95 AU. All 3 are underway or feasible because BB stays far, bright enough, and structured enough to measure carefully. That's the paradox that knits curiosity to anxiety. There is nothing wrong with BB's wake-up, but something is humbling about how quietly a galaxy can move a mountain, and the hook remains standing after the footnotes. A 100-kilometer class comet, already glowing in CO beyond Saturn's orbit, inbound on a near-perpendicular path, set by forces older and larger than our system. If it slept for billions of years, the answer to what touched it is not a single finger, but a slow tide, and, perhaps, a passing star hands you can't feel, working on times you don't live, leaving a trace you can now see. It breathes like a volcano, but it's not alive. If a comet can breathe, the breath is gas slipping through ice, not lungs but pores, not lava but volatiles that turn to vapor in the cold. BBC, 2014, UN 271, is already exhaling carbon monoxide far beyond Saturn, and the pattern of that breath hints at an interior that isn't uniform rubble. Narrow jets changed over just 9 days in March 2024, mapped by ALMA together with a compact millimeter continuum from the nucleus. That combination structured outgassing at 16.6 AU, plus a bright, very large core, points to stratified layers and pockets that open and close, a monster built in sheets. Rosetta taught us what layering looks like when you get close. On Comet 67P, terraces and cliff books in Osiris images stitched into onion shell stratigraphy, coherent layers wrapping each lobe, most simply explained if the lobes formed separately with internal sheets and later merged. A decade of work since Masironi et al. Has kept that picture intact, even in 3D reconstructions of planes through the nucleus. Rubble pile does not mean featureless mush. Comets can preserve deep, ordered fabrics. If 67P tiny next to BB kept its layers through eons, a 100-kilometer class nucleus has even more room to store stratified ice and dust. Layers aren't just pretty geology. They control plumbing. Rosetta also traced dust jets back to yawning pits and sinkholes, surface collapses that likely exposed or connected cavities. Those pits were active, their walls retreating by sublimation. Some outbursts may have been sudden cavity roof failures. Translate that behavior to BB scale, and you have a simple, testable idea. Discrete co-rich pockets vent through specific pathways, creating narrow jets that evolve as illumination migrates, fractures creep, or roofs fail. ALMA's 2-epoch maps multiple collimated CO jets, rearranged within days, fit that template eerily well. Why layered monster, not uniform snowball? Thermophysics. In a porous, low-strength comet, heating penetrates only so far each cycle before it dies out the skin depth. On 67P, diurnal skin depth is just a few millimeters, and seasonal depth reaches decimeters to meter scales. Deeper layers remain cold storage. Add BB's massive size and low thermal inertia, properties typical of comets, and you get a natural cold trap. Hypervolatiles like CO and CO2 can survive below a shallow, dust-rich mantle. Nudge the perihelion inward over geologic time, and those volatiles begin to reach the threshold where vapor pressure can thread inherited cracks, grain boundaries, or cavity networks. Suddenly, the breath appears lines in a radio spectrum long before water takes over. Cryovolcanism is the right analogy with an asterisk. On icy moons, the term means true geologic extrusion of liquid or vapor through conduits. Enceladus. Plumes. Triton's vents. Comets don't have global oceans or tides to pump them, but the physics rhymes. Gas generated at depth finds pathways to space, entraining dust and carving pits. ESA and NASA reviews define cryovolcanism broadly as the extrusion of materials that would be frozen at the surface. Comet jets, powered by sublimating volatiles, fit the spirit, if not the machinery of Europa or Enceladus. The point is metaphorical clarity. BB's breathing is volatile transport through a fragile, fracture-rich body, not biology. Layering also explains the choreography of on and off. If vents are tied to fixed topography in a layered shell, their position angles should repeat with rotation. If activity migrates across the season, we should see slow drifts as the subsolar latitude marches. ALMA caught jet geometry changing across March 817, 2024. The next step, more epochs across changing phase angles, should tell us whether we're watching rotation-locked throats, seasonal illumination, or the birth and death of fractures. Because BB is bright and distant, we can collect that timeline without the chaos of near-sun outbursts swamping the view. Inside the layers, pressure does quite work. Thermophysical models now reproduce global dust, H2O, CO2, and CO rates, by allowing gas pressure to build beneath a sealing crust of pebbly grains. When pressure wins, crust lifts and vents, then reseals as grains settle an ejecting crust cycle. In a giant like BB, gravity modestly strengthens that cap, so the cycle may favor narrow, long-lived vents over wholesale blistering. The observable consequence is exactly what radio maps can see: slender jets, not diffuse hemispheres, and repeatable kinematics if the vents persist. And the mantle itself? Rosetta saw dust mantles thicken toward perihelion as ices retreated and grains lagged. Then thin as cliffs collapsed or fresh ice patches appeared. Low density to 500 kilograms, m to the power of -3, high porosity to 70–80%, and very low tensile strength is less than 100 pascals, make comet skins easy to rearrange. On BB's enormous nucleus, that same material palette scales into a more stable laboratory. Local collapses won't erase the world. They will write legible entries in a slow journal of vents, fans, and filaments. Those surface resets are how we read the stratigraphy from the outside in color slopes, polarization changes, and morphology that betray grain sizes and layering just beneath. Put the pieces together as a working interior sketch you can falsify. A dust-rich lag mantle blankets layered ices. Below it, pockets and sheets of CO2 survive from formation. Heat waves penetrate millimeters daily to decimeters, meters, seasonal, turning on only the shallowest supplies at today's distance. Gas finds inherited planes, the onion shells, joints, and cavities. Pressure episodically pries open vents, ejecting dust and collimating jets. Rotation and season modulate which layers and vents engage. Collapse events, pit growth, rewire the plumbing on human timescales. Every line of that sketch has a measurement attached to it in 2025, 2031. Radio lines, COJ equals 2, 1, and their widths divided by positions for kinematics. Continuum plus optical for thermal size, albedo, and dust. Long baseline imaging for repeatability of jet angles. And, eventually, polarization and color to read the dust's handwriting and, by proxy, the layering just below. Nothing here requires special pleading. The size and mass that Hubble framed in 2022 tell you why the signal is strong and the structure resilient. The ALMA detection at 16.6 AU tells you which volatile is breathing now, and that the breath isn't uniform. Rosetta's decade of close-up geology tells you that layered, cavity-rich interiors are normal for comets, and that pits, vents, are how the inside speaks. The wonder isn't that BB behaves strangely. It's that we're watching a familiar script performed on a cathedral-sized stage. Two cautions keep the wonder honest. First, cryovolcanism is an analogy, not a diagnosis. Comets lack the deep reservoirs and tides that power icy moon geysers. We're seeing sublimation-driven venting through stratified media, not tectonics. Second, interior layering does not mean we can read composition like tree rings from afar. We infer it from surface change and gas, dust ratios. Where we can't yet connect a vent to a layer, we'll say so. Where a number is a model, not a measurement, we'll label it. That's how you keep mystery from becoming myth. So when you hear layered monster, picture a body that keeps its breath long and quiet. A nucleus to 137 kilometers wide, sheathed in mantles that open and heal, exhaling CO through throats that rotate with the world, and changing fast enough that a week matters. It is not alive. It only looks like something with lungs because physics found a way to make rock-weak ice behave like tissue flexing, resealing, sighing in sunlight. In the next part, we'll step outside the skin and let the light curve speak. How angles and time reveal grain sizes, how polarization betrays texture, and how the breath writes a diary you can read with a telescope. Nothing in our models predicts this thing. Strictly speaking, planetesimal theory can make 100-kilometer bodies. What the models don't predict comfortably is this combination. An intact, volatile-rich nucleus roughly 137 kilometers wide, coming from the Oort Cloud, already venting CO in deep cold, and giving us a long, clean look before it ever nears the inner system. It's not impossible. It's just lodged in the sharp corner where several expectations meet and creak. Begin with the baseline we thought we knew. Observationally, most comet nuclei are small single-digit kilometers, with a size-frequency distribution that falls off steeply toward larger radii. That's why a 100-kilometer class nucleus feels wrong in the gut. The catalogue primes you for pebbles, not provinces. Hubble's April 2022 result put BB's nucleus near 85 miles to 137 kilometers and framed a mass around 5 times 10 to the power of 17 kilograms, about 50 times larger than typical comet cores, and 5 times the mass of an average inner system comet. That isn't a flourish. It's the measured outlier that forces everything downstream to adjust. Formation physics shouldn't rescue your intuition here. It should complicate it. Modern reviews describe a pathway in which dust concentrates by streaming instability and jumps directly to 10 100 kilometers planetesimals, big from birth, not grown by endless sticking. Those primordial blocks are then scattered, heated, and sometimes exiled. In parallel, Oort Cloud simulations show a messy infancy for the solar system, where planetary scattering, neighboring stars, and the galaxies tied together populate a distant, nearly isotropic reservoir. Read together, these two pillars say, 100-kilometer icy bodies can form, and some can be thrown outward. They do not say those bodies should be easy to keep cold and volatile rich for billions of years. That's the discomfort. Interior physics deepens the crease. Early radiogenic heating, especially from short-lived 26 Al, can warm large icy bodies enough to restructure them, drive phase changes in ice, mobilize volatiles, compact pore space, and in some scenarios even cause partial differentiation. Classic thermal models show that for tens of kilometers radii and early formation times, 26 Al dominates the heat budget. More recent thermophysical work extends this to a range of compositions and porosities. If BB formed early and big, it should have felt that furnace. Yet ALMA sees strong CO at 16.6 AU hypervolatile inventory alive and venting now. Those two truths can live together, but only if the interior keeps cold traps or retrapped volatiles after migration. That's a narrow needle to thread. Surface geology doesn't let you shrug this off as just rubble. Rosetta's close work at 67P showed terrace onion stratigraphy and pits that behave like vents, evidence for ordered layers and plumbing, not uniform mush. Upscale that to a nucleus to 137 kilometers across, and the layered mantle picture becomes more, not less, plausible. But plausible isn't the same as predicted abundance. Thermal models for planetesimals suggest substantial processing compaction, volatile redistribution. In large bodies, BB tells us that even if processed enough CO survived or reconcentrated to light up far beyond Saturn, that combination doesn't violate any single paper. It stresses the joint where several papers meet. Then there's the population question, the mass distribution tale. Surveys and in situ missions have biased us towards small, short-period comets. The observed size distribution slopes strongly, making giants rare by construction. BB forces a re-audit of the far tail. Either the Oort Cloud contains more 100-kilometer relics than our priors assumed, or our discovery methods have been blind to them until very recently, or both. Nothing breaks if a few such giants exist. What bends is the inferred inventory and the collisional thermal histories we assign to it. A single data point shouldn't rewrite a population, but an extreme data point should move the error bars. Protoworld is a tempting label and dangerous if you let it run loose. BB is not a dwarf planet. It's an icy planetesimal at the upper end of what comet science is used to touching. In formation language, though, it is exactly the scale of original building block that streaming instability models produce. If a few objects of this size were launched into the Oort Cloud early and escaped heavy collisional grinding, they could persist. That's a coherent story. It just wasn't the one most of us carried around in the front of the mind when we said comet. The theory didn't forbid BB. The theory failed to make you expect it. Now stitch chemistry back to its origins. A robust correlation has emerged between nucleus size and CO. H2O abundance across comets' bigger nuclei tend to carry, emit more hypervolatiles, consistent with re-entrapment and retention in near-surface amorphous ice layers. That trend gives BB a narrow theoretical lane. If it formed large and cold, retained amorphous ice, and avoided long inner system passages, it could keep CO lakes and pockets capable of venting at 1617 AU. It's a lane. It's just tight. Another reason the object feels like a test rather than a trophy. So why call it the comet that shouldn't exist? Because BB exposes three tensions at once. 1. Scale versus catalogue. Largest measured comet nucleus ever measured, not inferred, parked against a literature dominated by kilometre-scale bodies. The outlier is real. The sample may be biased. Both can be true. 2. Heating versus inventory. Early 26 AL should have processed big interiors. ALMA shows CO alive and structured today. Retention, retrapping must be efficient, or formation late enough to square that circle. 3. Population versus expectation. Oort Cloud formation allows big exiles. Our mental model didn't expect to see one this intact and this active. The cloud's giant fraction and thermal histories need tighter bounds. What resolves the discomfort isn't a slogan. It's measurements we can actually do before 2031. Seasoned CO mapping. Multi-epoch COJ equals 2-1 kinematics to see whether jets are rotation-locked throats or migrating seasonal vents, testing the layered mantle plus cryovolcanic plumbing picture against time. Thermal inertia constraints. Joint fits to millimeter, infrared continuum, and optical light curves to bracket conductivity and porosity inputs that set how far early radiogenic heat and modern solar waves penetrate. Population priors. Fold BB into size distribution models with explicit selection effects. Ask what number of BB-class objects is consistent with survey limits. If the allowed number isn't 0, the paradox softens. Here is the honest place we land. Theory did not break, but it did blink. We can make big icy building blocks. We can exile some to a distant reservoir. We can keep volatiles if the history is gentle and cold. BB is where all three can stack in a public, measurable view. That makes it less a contradiction than a calibration target, an object that turns footnotes in formation papers into parameters we must now pin down. So yes, the line stands. Nothing in our models predicted this exact thing. Here, now, with these properties. But the models gave us all the parts. BB assembled them in a way that forces us to reweight the priors. Scientific discomfort is the right emotion. It keeps us from mistaking familiarity for truth, and it keeps the next piece of the puzzle honest when it slides into place. If 3I, Atlas, was the anomaly, BB is the aftermath. Start with the timeline we're living in. In late 2025, the third confirmed interstellar visitor, 3I, Atlas, swept through the inner solar system on a hyperbolic arc, Perihelion, near 1.4 AU around October 30, and a safe miss of Earth at about 1.8 AU. That alone puts it in the same historical breath as 1I, Oumuamua, and 2I, Borisov, rare travellers from other stars. Then the radio result arrived. Meerkat detected hydroxyl at the 18 cm lines, 1,665, 1,667 MHz, a canonical cometary signature produced when sunlight dissociates H2O and leaves OH to imprint the spectrum. That single detection reset the debate about its nature from maybe engineered to actively outgassing water like a comet. Now, place BB beside it, not to crown a winner but to scale our questions. BBC 2014 UN 271 is the largest comet nucleus ever securely measured, about 137 kilometers across, by Hubble's 2022 analysis. With a mass around 5 × 10 to the power of 17 kilograms, 500 trillion tons. That size is to 50 times larger than most known comet cores, and framed as to 100,000 times the mass of a typical inner-system comet in the Hubble release. The contrast is blunt. Whatever the exact size of 3I, Atlas's nucleus turns out to be, it is orders of magnitude smaller than BB. Put simply, 3I, Atlas sets context, BB sets the ceiling. Velocity profiles underline the difference between from here and from away. 3I, Atlas, orbit is unbound with a high eccentricity and velocity at infinity. V infinity is approximately equal to 57 kilometers per second in early analyses textbook interstellar kinematics. The NASA overview pins the geometry. Perihelion, at to 1.4 AU, no threat, outbound to the dark. BB, by contrast, is an Oort Cloud emissary on a near perpendicular slightly retrograde ellipse, with perihelion much farther out at 10.95 AU in January 2031. One tears through the inner system fast. The other offers a long, cold laboratory. Different clocks, different experiments. Chemistry separates them in a second way. For 3I, Atlas, O, at 18 centimeters, is the giveaway that water photochemistry is active near the sun normal for a warming comet. For BB, the engine is on in the deep freeze. ALMA mapped CoJ equals 2, 1 at 16, 6 AU in March 2024, and saw multiple narrow jets evolve over 9 days, with a compact millimeter continuum from the enormous nucleus. Water is quiet out there, CO leads, so while both comets are alive, they breathe different gases under different lights. 3I, Atlas hot and close, BB cold and far. Context needs more than one foil. 2I, Borisov, the first clearly comet-looking interstellar object, carried a tiny nucleus constrained by Hubble, and dynamics 2 is less than or equal to 0.5 kilometers. Oumuamua, the first interstellar visitor, likely had an even smaller effective size and famously odd non-gravitational acceleration. Set those beside 3I, Atlas, interstellar, active, perihelion inside Mars, and BB Oort Cloud giant, active far beyond Saturn. The point is not that one is stranger than the other. It's that our observing decade spans extremes. Sub-kilometer interstellar specks to 100-kilometer Oort Cloud monument. That range is what lets us ask population-level questions with a straight face. Mass ratio is the phrase that tempts headlines, and it's where we draw a line. BB's nucleus mass is framed from Hubble's measurement. For 3I, Atlas, nucleus size and mass remain uncertain in peer-reviewed literature. Any quoted BB, 3I mass ratio would be speculation. I cannot confirm this. What we can say cleanly, BB's to 137 kilometers nucleus dwarfs 2I. Borisov's is less than or equal to 0.5 kilometers nucleus, and dwarfs plausible estimates for 3I, Atlas, as presently constrained, while 3I, Atlas's interstellar speed, profile v infinity, 57 kilometers per second, marks it as unbound. Use each object for what it can defend. BB for scale and stratified activity in the cold. 3I, Atlas for interstellar kinematics, and near-sun chemistry with a radio-clean OH detection. Why pitch them together at all? Because each fixes a blind spot in the other. Interstellar visitors zip by on short schedules. They show us how star-to-star debris behaves but deny us long baselines. Oort emissaries like BB move slowly at safe distances. They let us watch the physics settle, how jets repeat or migrate, how non-gravitational terms accumulate, how dust-sized distributions evolve with phase angle, yet they tell us little about material born around other suns. Tie them, and you get a fuller sentence about comets as a class. What changes with birthplace? What doesn't? Micro-hook kinematics as truth serum. 3I. Atlas's hyperbolic excess is not a mood, it's a measurement. V infinity and A1 say unbound without adjectives. BB's element's inclination is approximately equal to 95.5 degrees. Q is approximately equal to 10.95 AU, Tisserand parameter with Jupiter, far from the Jupiter family save first-time Oort arrival. Those labels matter because they set priors for everything downstream. Expected gas species at given R, jet longevity, and the odds that a close planetary kick will muddle tiny thrusts we're trying to isolate. Read the orbits first. It makes the rest honest. Micro-hook radio as referee. 18 centimeters isn't exotic. It's cometary housekeeping writ in radio. Meerkat's dual-line detection for 3I. Atlas did what good data do. Collapse speculation to the space the spectrum allows. That is useful beyond this object. It sets a standard. When the next interstellar visitor skims inside 2AU, book the 18 cm window early. If there's water, the sky will tell you in a narrow band, and you won't have to argue with metaphors. Micro-hook CO as cold memory. ALMA's co-maps for BB give us kinematics in the regime where water sleeps. Jet position angles, line widths, and evolution over days. Repeat that across seasons to see if vents are rotation-locked throats in a layered mantle or migrating seasonal fractures. That's not trivia, It's theory calibrating detail we rarely get for a target this big, this early. With those pieces, here's the working synthesis you can test. Interstellar benchmark 3.1. Atlas, hyperbolic visitor, with V infinity, 57 km per second, perihelion, to 1.4 AU, O18 cm detection confirming water-linked outgassing near the Sun. Nucleus size, mass not yet secure. Use it to anchor how fast, how active, how coloured an interstellar comet looks under inner system heat. Oort Cloud benchmark, BB, bound, near perpendicular orbit, perihelion, to 10.95 AU in 2031. Hubble nucleus to 137 km, record-setting. Co-bright jets at 16.6 AU. Use it to anchor how stratified, how persistent, how measurable deep cold activity can be. Population bridge, 2.1, Borisov. Interstellar, small nucleus, is less than or equal to 0.5 km. Classical coma, and tail proof that star-to-star debris can look ordinary in morphology while being dynamically extraordinary. Everything we say next in this film leans on that triad. When we argue that BB stresses formation and retention models, we're not waving our hands, we're pointing at a 100-kilometer nucleus that stays active in CO beyond Saturn, sighted. When we insist that interstellar visitors demand rapid, radio-first campaigns, we're not scolding, we're showing an OH spectrum that settled a month of noise, sighted. When we refuse to quote a BB3I mass ratio, we're not being coy, we're labeling what the record does and does not yet support. What it adds up to is simple and humbling. 3I. Atlas reminds us how fast another star's crumbs can move, and how quickly rumour collapses under a narrow spectral line. BB reminds us how slowly a monument can breathe, and how much you can learn when a comet gives you time. Between them stretches the decade's most valuable baseline. From meters to hundreds of meters, interstellar bodies to a 137 km Oort giant. From hot water OH at 1.2 AU to cold CO jets at 16-17 AU. From rush to watch. If you want a benchmark, you have two. Carry that forward, because Part 8 asks whether these arrivals are isolated flukes or the visible edge of a pattern. If 1 is weird and 2 is a coincidence, 4 might be something else, and the catalogues we're building now are finally large enough to test that without superstition. For the first time, we can compare like with unlike, and let the sky, not our priors, decide how often impossible should really mean rare. 1 is weird, 2 is a coincidence, 4 is something else. We want the sky to be random, comfortable drizzle, not patterns that whisper intent. But the more our catalogues grow, the less isolated fluke feels like a safe default. Long-period comets, LPCs, are fed inward by the slow hands of the galaxy and by passing stars. Those mechanisms don't deliver a steady clock. They deliver lulls and gusts, quiet decades, then clustered arrivals that look like a mood swing in the dark. Modern dynamics papers model exactly this, a background trickle from the galactic tide, punctuated by showers and drizzle episodes after stellar nudges. The upshot is uncomfortable. Bursts are expected. We just didn't have the statistics or the cadence to see them cleanly until now. Microhook showers happen. Numerical work shows that when a star skims the Oort cloud, the inward flux of new comets can spike for thousands to millions of years, superposed on the ever-present tidal feed. You see this in simulations from multiple teams. The galaxy's vertical tide sets the baseline. Encounters sculpt short-lived, real enhancements. BB does not require a named culprit, but its era lives on a landscape where clusters aren't shocking, they're baked in. Where dread creeps in is the pattern hunt. Human eyes love lines. Science insists on causes. Claims of planes or streams among LPC perihelia have appeared for decades, sometimes invoked to argue for hidden perturbers. But reviews remind us how treacherous those claims can be. Discovery catalogues are riddled with directional, seasonal, and sociological biases. Northern observers, ecliptic-centric surveys, twilight gaps, and magnitude limits, all of which can manufacture false clustering. Even without conspiracies, selection effects can stack dots into arrows. Any pattern you keep must survive a bias audit. So what would real clustering look like? Not a perfect line, a statistical excess. After a stellar graze, Long-period comets injected from similar source regions of the cloud arrive with related energies, and directions spread over long windows. Rickman's review describes exactly that picture: major showers with lingering drizzle, while later work quantifies how the tide and encounters jointly shape the flux. In other words, physics predicts families of arrivals, not immaculate geometries. The test is whether our growing catalogues, debiased, still prefer burst to flat. Enter the surveys. Rubin Observatory's decade-long cadence, LSST, is designed to break discovery bias by patrolling the whole sky deeply and repeatedly. Forecasts suggest LSST would have found a large fraction of known comets years earlier and at roughly double the distance. Other analyses project at least a twofold increase in long-period, hyperbolic comet discovery rates as a class. Regular revisits, uniform depth, and all-sky coverage mean the northern winter ecliptic hugging bias weakens. If clusters are genuine, LSST should make them stick. If they dissolve under even coverage, they were artifacts. Either way, the anxiety gets an answer. Microhook, we've been flying half blind. MNRAS work on catalogue biases, catalogue the traps, more northern observers than southern, diurnal visibility windows, sky sectors that are simply harder to search, plus sociology who looks where, when. A simple model reproduces much of the mystery clustering from geometry alone. Rubin doesn't cure everything, but it crushes the worst offenders by design. Where does BB sit in this? As a data point, it doesn't prove a cluster. As a type specimen, a giant. CO active Oort emissary arriving in the same decade as 1I, 2I, and 3I, it forces us to ask if the edges of our comet population are lighting up together because our eyes finally got good, or because the faucet upstream twitched. Dynamics is agnostic about spectacle. The tide breathes, stars pass. Fouchard and colleagues show how the memory of initial Oort Cloud structure can linger in the statistics of new LPCs. Other groups show how encounters seed temporary excesses. The tools are there. The catalogues are catching up. Resonance enters the conversation with caution. For short-period families, resonances with planets organize orbits into clear architectures. For first-timers from the Oort Cloud, planetary resonances don't shape the injection. They only nibble at survivors on the way out. If you see repeated longitudes or inclinations among truly new LPCs, look upstream cloud, anisotropy under the galactic tide, or the directional fingerprint of a past stellar pass before you invoke resonances or a hidden planet. Well, test the invisible shepherd idea in the next part, where it belongs. Microhook dread is a statistic, not a story. Suppose a dozen new LPCs over a few years share unusually similar original energies and a sky patch after bias correction. In shower models, that's not a ghost. It's the footprint of a past encounter. The anxiety you feel is appropriate. Clustered inward traffic means our long quiet between big perturbers is not a guarantee. It's just the last chapter. But we balance that with a different unease. Overfitting. Papers arguing for perihelion planes or zones exist, and so do rebuttals pointing to discovery bias and small number statistics. A responsible script keeps both in view. We can point to ongoing, peer-reviewed work re-examining LPC distributions with modern injections and bias models. We can admit that some claimed clusters probably won't survive LSST. Dread without discipline is just a vibe. Our job is to let uniform data decide. Here is the operational plan that turns suspicion into measurement. Debias the stream. Use LSST-like cadence simulations to reweight the discovery probability of LPCs as a function of sky position, season, magnitude, and rate of motion. Then test for clustering in the reweighted sample, not the raw list. Fast methods to quantify survey selection already exist and are being applied. Tag energies and directions. Work in original barycentric 1, A and inbound direction on the celestial sphere, with uncertainties. Genuine showers produce excesses in those coordinates that persist beyond cosmetic plane fits. Cross-match with encounters. Use Gaia-era catalogues of stellar flybys to see whether statistically credible past encounters line up temporally with any observed excess, allowing for long lags from injection to perihelion. If nothing matches, the tide alone may suffice. Watch the denominator. Rubin's first seasons will double, or more, the discovery rate of distant inbound comets. If an apparent cluster grows weaker as the catalogue expands, it was biased. If it strengthens, you have physics. So is something else true today? Caution says, not proven yet. Theoretical groundwork expects bursts. Early messy catalogues easily fake them. Next-gen surveys will adjudicate. What the present decade does deliver is an unnerving span. Oumuamua and Borisov from other suns, 3I, Atlas with radioproof water in the inner system, and BB, a cathedral-scale comet, already breathing CO in the cold. Individually, each is explainable. Together, they dare us to test whether the faucet upstream just opened a notch. And that's the dread worth keeping. Not that a hidden hand is steering comets at us, but that we've lived through a biased, shallow census and told ourselves a soothing story about randomness. The galaxy and its stars don't keep our schedule. If the Oort Cloud is exhaling in pulses, we will see it soon uniformly, repeatedly, with enough statistics that weird can finally mean rare, and cluster can finally mean real. Until then, we hold BB not as a smoking gun, but as a bright page in a ledger that LSST is about to thicken. Next, we test the most tempting explanation for patterns with a pull, the unseen shepherd. If a massive, distant body really tugs comet paths into favoured directions, its signature should survive a bias purge and outcompete tide and star models. Well, put that idea on the stand fairly, with citations, and with all the ways it could be wrong. We still haven't found it, but it keeps pulling strings. Suspicion starts with a picture. A super-Earth, hundreds of astronomical units out, slow and dim, quietly talking the Kuiper belt into strange order. That picture, Planet 9, was proposed to explain why a handful of distant trans-Neptunian objects, TNOs, seem to share peculiar alignments that 8 known planets couldn't maintain on their own. In dynamics, alignment rarely survives without a shepherd. The claim was that a 510 m body on an eccentric, inclined 400-800 AU orbit could be that shepherd. The counterpicture is biased. The Outer Solar System Origins Survey, OSS, showed explicitly, and with survey pointings and depths in hand, that detections of extreme TNOs suffer strong, non-intuitive selection effects. When you forward model those effects, an apparently clustered sky can come out of an intrinsically uniform population. Their independent sample of large objects was consistent with no true angular clustering. That doesn't disprove a planet. It removes the necessity of one from that dataset. The debate hasn't ended at the blackboard. It has moved to the sky. Wide-field searches have chewed steadily into the parameter space where such a planet could hide. Cassini, ranging constrained, where a massive distant perturber cannot sit without spoiling the exquisitely measured timing of Saturn, already ruling out large swaths of true anomaly for canonical P9-like orbits. Later, Ephemeris work with INPOP-19, A pushed it further. If P9 exists, a 5 ME version must lie 500 AU away. A 10 ME version, 650 AU. Closer, and the solar system's timing would have been noticed. Optical surveys have joined in. ZTF, DES, and now Pan-STARRS-1 have each run targeted searches using bias-corrected synthetic P9 populations. The most recent PS1 analysis, accepted 2024, reports that combining PS1 with prior ZTF and DES work rules out roughly 78% of the Brown and Batygin parameter space to V is approximately equal to 21.5, with the surviving regions pushed fainter and inconveniently close to the galactic plane. Translation: if P9 sits where the original fits liked best, it's increasingly constrained not to be bright, easy. On the other side of the scale, proponents argue the clustering remains significant after updated bias modeling, and that a P9-like configuration still best explains multiple features at once. Perihelion longitudes, orbital poles, highly inclined objects, retrograde centaurs. The hypothesis hasn't been falsified, it has been trimmed and relocated. The key point for us is epistemic. Absence in these searches narrows options. It does not yet close the case. What does any of this have to do with BB? Less than suspicion wants, more than zero. Planet 9 dynamics primarily reshape the trans-Neptunian region detached orbits, long-lived alignments, production of odd inclinations by slow secular torques over hundreds of millions of years. The standard injectors for Oort Cloud, long-period comets like BB, remain the galactic tide plus random stellar flybys. That machinery alone reproduces an almost isotropic inclination distribution and a steady trickle of first-timers. In that baseline, you don't need P9 to steer BB in, and no peer-reviewed study has tied BB's specific orbit to a P9 perturbation. I cannot confirm such a link. Still, a distant super-Earth, if real, could add texture. A P9-like body can torque the inner Oort cloud and extended scattered disk, altering the energy, angular momentum phase space that eventually feeds long-period comets. That influence would be statistical and slow, not a kick that singles out one comet. If Planet 9 exists, it could modulate long-term supply. It is unlikely to be the proximate cause of BB's present 95 degrees path and co-bright wake-up at to 1617 AU. BB looks exactly like what the tide and stars injector orders. Where the hypothesis stands today, in 4 lines you can verify. Motivation, distant TNO alignments, and odd inclinations admit a super-Earth solution. The canonical mass, orbit, 510 A is approximately equal to 400-800 AU. E is approximately equal to 0.2-0.5. I is approximately equal to 1525 degrees. Counterpoint. OSA's and DES bias analyses show that small number survey bias samples can mimic clustering. DES finds no significant angular clustering in a controlled 14 etno set. Search status. Cassini in-pop ephemerides exclude closer, heavier P9 realizations. ZTF plus DES plus PS1 collectively rule out most of the brighter, easier sky where P9 could have been. Bottom line. Unequivocal detection is pending. Non-detection has narrowed the map. The burden of proof now rides on the faint, crowded regions left to probe, so we hold 2 truths without forcing a third. Planet 9 remains a live, testable hypothesis for Kuiper Belt architecture. BB remains an Oort Cloud emissary, whose journey is cleanly explained by galactic tides and the occasional passing star. If a hidden shepherd exists, its pull on BB is at most background, not the hand on the tiller. Our suspicion is healthy. Our script stays disciplined. Where data is narrow, we say so. Where links to BB are speculative, we don't pretend otherwise. Next, we widen the frame from hidden planets to hidden mass. What if the tug we're feeling isn't a world at all, but clumping in the dark, granular dark matter, or another phantom force that bends orbits without offering a disk to photograph? Well, test that idea with the same rulebook. Mechanism first, citations on the table, and a clear path to falsification. If you wanted to hide something, a comet is the perfect disguise. The suspicion writes itself. A dark object drifts in from the deep, breathes through narrow jets, and keeps structure at a distance where sunlight is weak. If you were engineering a messenger to pass quietly through a system of curious primates, would you not wrap it in ice and dust and let physics do the theatre? That's the romance. Our job is to test the romance until only the measurements remain. First, the positive case, the things that would make the whisper theory worth time on a whiteboard. You look for unnatural regularities that survive instrumentation and geometry. Narrowband radio transmissions, Hertz-wide carriers that nature rarely makes, repeating specular glints like polished facets catching the sun, or phase-locked optical modulations, too crisp for a porous, venting world. SETI has spent decades tuning pipelines to exactly such techno-signatures, spikes so spectrally thin that they scream transmitter, not plasma. If you want a heuristic, broadband is often nature. Hertz-wide is a machine's accent. Then there's light itself. Artificial surfaces can betray themselves by mirror flashes, specular reflections that ride atop a rotational light curve as sharp, punctual spikes. It's not science fiction. Specular glint frameworks are now proposed even for exoplanets and are routinely studied for satellites in Earth orbit. If something glossy hides in a coma, the tell would be an optical transient, too clean and too repeatable for dusty topography. We haven't seen that for BB. But the test exists, and the cadence to try it exists. Now, the record we actually have. Hubble's analysis put BB's nucleus near 85 miles to 137 kilometers across and to 5 times 10 to the power of 17 kilograms. the largest comet nucleus ever measured with confidence. That single, load-bearing result is exactly what you'd expect for an extreme, natural planetesimal, exiled to the Oort Cloud early, then stirred sunward. Nothing about the measured size or albedo black as charcoal, typical for comets, suggests engineered surfaces. Everything about it shouts big, cold, porous. Spectroscopy is louder still. In March 2024, ALMA mapped carbon monoxide emission, the COJ equals 2, one line, at 230 GHz, from BB at 16.6 AU, and saw multiple narrow jets evolve over 9 days. That is textbook hypervolatile physics in deep cold. CO switches on where water sleeps, threads, fractures, and vents. It is not an antenna, it is a freezer-reaching threshold. If you're hunting whispers, ask for radio carriers that are not molecular lines first. What ALMA saw is chemistry, not code. Geology weighs in by analogy. Rosetta's close work at 67P showed onion shell stratigraphy, terraces, pits, and sinkhole-borne jets, the plumbing set that turns sunlight into collimated breath. Active pits grow and reseal, fractures open and heal, dust mantles rearrange. BB's CO jets look like that behavior writ large. The whisper theory would have to explain why an engineered object mimics and needs to mimic every messy hallmark of layered, low-strength comet interiors. It's possible in principle, it's unparsimonious. What about structured light curves? Then the claim that repeating photometric signatures imply machinery. Be careful. Rotating, irregular nuclei with fixed vents can produce highly structured, repeatable modulations in brightness and polarization, especially when jets are collimated and the observing geometry changes slowly. That is the expected outcome of natural topography and layered plumbing. Before structure equals design, pass the curve through the gauntlet we learned from Rosetta. Look for rotation-locked jet position angles, seasonal drifts tied to subsolar latitude, and color, polarization signatures consistent with dust, not metal. Layered ice plus dust can write a tidy curve, no conspiracy required. Radio again, because the word signal is magnetic. When astronomers say we detected OH at 18 centimeters, in comets, that means sunlight is cracking water, and the hydroxyl radical is singing at 1,665, 1,667 megahertzes, a natural beacon we've used for decades to measure water production. That's how 3I, Atlas, earned its It's a Comet badge. A genuine techno-signature would look different. A narrow carrier, Doppler coherent with the object, persisting across on-off pointings and re-observations, and sitting away from known molecular lines and human interference. We have no such carrier from BB. I cannot confirm this. Still, skepticism has to cut both ways. Could a non-natural interior hide under a thick coma and dust mantle, using sublimation as cover? Conceivably, but every extra assumption costs plausibility. To keep time with the data you would need: 1. A 137 kilometers class shell, whose bulk, albedo, color, and thermal behavior match carbon-rich cometary material. 2. A vent network whose kinematics reproduce natural CO line widths and evolving jet position angles at 1617 AU. 3. No narrowband transmitters anywhere obvious in the spectrum. And 4. No specular flashes inconsistent with dusty microphysics. That's an elaborate mask to achieve what a real comet already does for free. Occam keeps the straight face here. So the responsible posture is fascination with a ruler. Here is that ruler 5, falsifiable checks that would move Whisper from romance to work order. 1. Narrowband carriers. Search for Hertz-wide lines that track BB's barycentric Doppler precisely and persist on re-observation, away from molecular transitions and RFI. SETI pipelines, turbo SETI, machine learning anomaly filters are built for exactly this. None are reported for BB. 2. Specular glints. Run high-cadence photometry looking for sharp, angle-specific spikes that repeat with rotation and phase signatures of polished facets. Satellites near Earth show them routinely. Comets generally don't. None reported for BB. 3. Non-gravitational anomalies without gas. Detect sustained accelerations inconsistent with observed outgassing or dust. Oumuamua provoked that debate. BB is literally CO bright, so thrust is expected and testable against spectra. Current evidence says gas explains the push. 4. Non-cometary composition, find lines, continua, or polarization inconsistent with known cometary inventories. Optics, for example, metallic spectral features in emission, unnatural thermal emissivity. So far, BB's signals read as icy, dusty, and cold. 5. Impossible geometry. Observe light curve or jet geometry that refuses any rotation. Season. Vent model. Rosetta's playbook explains a lot. BB would need to do more than look tidy. It would need to contradict that playbook cleanly. What survives after that gauntlet is the quiet, less glamorous truth. BB is an enormous, charcoal-dark cometary nucleus with a natural volatile engine already on in the cold. Its jets change over days. Its size, albedo, and likely porosity fit the family. Its orbit screams Oort, not artifice. Hubble's numbers make it a monument. ALMA's line makes it breathe. Rosetta's geology makes its behavior unsurprising at the cathedral scale. None of those facts needs a designer. All of them need time at the telescope. If the whisper theory has value, it's as a discipline generator. It forces us to define artificial in operational terms before we go looking. Carriers, glints, impossible accelerations, non-cometary spectra. It forces us to publish non-detections as loudly as detections. It forces us to admit what we cannot confirm and to label speculation as such. In a decade when genuine anomalies do appear interstellar v infinity, odd non-grav terms, strange polarization, those habits keep wonder and rigor on speaking terms. So yes, if you wanted to hide something, a comet is a perfect disguise. That's precisely why comets are terrible disguises in practice. Up close, they are loud, with chemistry, geometry, and dust. BB is loud in exactly those ways. The romance isn't banned. We can keep an ear out for a carrier and an eye out for a glint, but the story that earns its place in the ledger is the one that matches the lines we can point to today. Next, we widen the suspicion from worlds to shadows. Not a shepherding planet, not a whispering probe, but mass with no face, dark matter clumping, or a phantom force showing up as gentle tugs where no planet stands. If a shadow is pulling strings, it must leave a gravitational signature that BB can help us weigh. That's where we're going. We can see it, but we probably won't touch it. The heartbreak starts with geometry. BB's path is wrong for us in all the expensive ways. A near perpendicular orbit, inclination is approximately equal to 95.5 degrees, that slices through the planetary plane, and a perihelion far from the Sun, Q, is approximately equal to 10.95 AU, around late January 2031. A rendezvous isn't just go fast and meet it, it's leave the ecliptic, climb to 95 degrees out of our traffic lane, and show up beyond Saturn's orbit with enough propellant left to match velocities. The public elements lay out the problem in two unforgiving numbers, to 95 degrees and to 11 AU. Delta V is where dreams go to die. Plane change burns scale with velocity and angle. A to 90 degrees inclination change in deep space is brutal unless you cheat with gravity assists. The classic playbook says, stack flybys, usually Earth-Venus, Earth-Earth, or an Earth-Jupiter express. Use the big planets as momentum banks, and shape the trajectory so most of the turn is done by gravity, not fuel. That's how we make impossible targets possible, but every assist needs time, alignment, and a patient launch window. The technique is real. NASA's own primers walk the math. Gravity assists trade momentum to add energy, and bend a path you could never buy with propellant alone. Time is the second wall. BB's best observing years cluster around its distant perihelion in 2031. Launching now to thread multiple assists and still arrive near Q demands a miracle of alignment or a willingness to accept a very late, very cold encounter well after perihelion. The alternative, skip the assists and brute force the plane change, is a non-starter for chemical propulsion at practical masses. Even a flyby needs luck. A high-speed pass at to 1012 AU with respectable phase angles for imaging, spectroscopy, and radio science, all while the target is venting CO and throwing dust. Rendezvous matching BB's, speed so you can loiter, moves from ambitious to borderline unless a heavy launcher, advanced propulsion, or an extreme gravity assist chain is on the table. Gravity assists can help, but the calendar is indifferent to our excitement. Power turns the screw again. At 211 AU, sunlight is to 1/121 of what it is near Earth. Solar arrays that are comfortable at Mars wheeze in this darkness. Even Junos' heroic solar mission to Jupiter worked at to 5 AU, not to 11. Out here, you plan for radioisotope power, RTGs that turn plutonium's heat into electricity, with steady output independent of sunlight. NASA's RPS program says the quiet part aloud. In the outer solar system, environmental conditions often preclude other electrical power sources. RTGs are the enabling option, and next-gen RTG designs exist precisely to keep deep space missions alive for decades. That's mass you must lift and heat you must manage both bite into the delta-V budget you wanted for the target. Every instrument rides inside those limits. A proper BB payload wants thermal IR to read the nucleus and dust, a sub-mm receiver for CO and other lines, narrow-angle optics to claw detail out of a small, dark nucleus, polarimetry and color to read dust handwriting, dust detectors to weigh grain sizes and speeds, and a robust comms system to phone home across is greater than 10 AU. The power and thermal budgets for that suite at to 100 and 120 W, nominal or more, scream RTG, not solar. They also scream deep space network time and large antennas. There's no cheap mode when photons are scarce. Just do a fast flyby then sounds easy until you list the hazards. A comet that's breathing at 16-17 AU, CO bright already, will likely still be venting at to 11 AU. Dust fans and collimated jets mean a non-zero grain environment. A high-speed pass trades proximity for safety. The closer you skim, the sharper the images and the stronger the line signals, but the higher the impact risk and the tighter the pointing and tracking tolerances. And because BB's orbit is almost orthogonal to ours, your relative velocity vector may leave you with sub-optimal sun-target spacecraft geometry for parts of the pass. You can design around this, but you pay in approach speed, standoff distance, or both. Could Jupiter save us? Maybe. A deep Jupiter assist is the only practical way to tilt onto a steeply inclined solar orbit without propellant bankruptcy. Classroom and mission design texts have shown for decades how successive planetary swing-bys can stitch together huge plane changes with modest burns, and there are even a Vega deep space burn plus Earth flyby strategies that reshape the outbound aim before the big assist. But you need the calendar to cooperate. For a target whose science peaks by to 2031 and whose geometry is this unkind, the alignment might not show up in time. That's how we can see it becomes we probably won't touch it. Suppose we accept it after perihelion. BB won't race off into the inner system. Its perihelion is already beyond Saturn, so the post-2031 arc still lives at to 1113 AU. A late flyby could still net gold. Nucleus dimensions from limb profiles, thermal inertia from day-night contrasts, CO, CO2, mapping to trace vent geometry, color and polarization to infer layering and grain sizes. The science case survives delay. The engineering case, power, mass, time, does not get easier. RTGs decay slowly but steadily, comms geometry may worsen, and public will is harder to keep warm for a target that's been and gone. Even if gone is just a few AU farther out. Why not a small sat rideshare? Because a small mass doesn't change geometry. A CubeSat with a star tracker and a science-grade spectrometer still needs delta-V to climb to 95 degrees and reach to 11 AU in time, still needs watts in the dark, and still needs thermal control that won't freeze the bus or the propellant. You can hitch a ride to a planetary flyby? Yes, but the leg that matters is the one after the assist, and that leg is where the physics bills you. What about exotic plays solar Oberth maneuvers or electric sails? A close sun Oberth burn at very high speed, near the sun to multiply effective delta-V, has powered credible proposals to chase interstellar objects, but it demands heat-tolerant stages and trajectories that dive sunward first. Even then, you are optimizing energy, not magically creating inclination. Electric or solar sails trade propellant for time and area. They like sunlight. BB lives where sunlight doesn't. The farther out you go, the worse the sail's acceleration. At to 10-12 AU, the promise fades with the photons. Communications is the quiet tax. At to 11 AU, round-trip light time is over 3 hours. Autonomy that's routine at Mars must be mandatory here. Sequences must survive without babysitting, Fault trees must end in recoveries that don't need ground in the loop. Link budgets require high-gain antennas, careful pointing, and DSN assets scheduled against every outer planet mission in flight. None of this is impossible. All of it is costly in mass, power, and calendar. If this sounds like moving the goalposts, it isn't. It's naming the field. BB is a superb observing target, precisely because it is huge and far. Hubble could weigh its nucleus. ALMA could map cojets at 6 AU. We can build an entire multi-year, multi-wavelength campaign from Earth and Earth orbit, with time to spare. Spacecraft proximity science would be transformative, but the cosmos hasn't arranged an easy door. The numbers that make BB a monument for telescopes to 137 kilometers wide, active in the cold, unthreatening distance, are the same numbers that starve a rendezvous of time, watts, and propellant. So what do we do with nearly impossible? We don't flinch. We pivot. We treat BB as the calibration target for everything telescopes can do when a comet gives us years. Seasonal CO mapping, rotation-locked jet geometry, non-gravitational terms in a quiet dynamical background, dust handwriting in color, and polarization across unusual phase angles set by that wild 95 degrees orbit. If a mission architecture appears that threads a Jupiter assist in time with an RTG-powered, slim payload, well, cheer it on. Until then, we drain every bit of physics the sky will hand us and publish the negative as hard as the positive, so the next giant that wanders in finds us ready. The frustration belongs in the record, but not as defeat, only as a clear constraint. We can see it, but we probably won't touch it is not a shrug. It is a boundary condition for honest planning. BB is telling us to finish the Earth-based playbook, to keep RTG lines healthy, to practice fast-turn gravity assist chains on nearer targets, and to write autonomy that respects 3-hour light time. The monument is distant. The work is here. It's waking up, and we're already late. Put a clock on the wall. Perihelion around 23 January 2031, at a distance of to 10.95 AU, still beyond Saturn's path. That date and distance aren't vibes. They're the live orbital elements maintained in public ephemerides. The inclination stays wild is approximately equal to 95.5 degrees. The Jupiter moid stays harmless to 6.1 AU, and the geometry screams observe from afar and do it on schedule. Everything about the science we want depends on showing up before that distant turn, then riding the outbound arc while the jets evolve. If we drift, we lose the cleanest part of the experiment. A comet this big is generous with signal but stingy with time. The Hubble result that set the scale to 137 kilometers nucleus to 5 × 10 to the power of 17 kilograms is exactly why we can learn so much at such large distances. The mass keeps the body coherent, and the size lifts the continuum above noise. But the same numbers mean the story will be written in slow, seasonal changes, not frantic near-sun fireworks. If we don't build those seasons into a calendar now, the cathedral we brag about will be a mural we only glance at. Microhook, the chemistry's already on. We are past the moment of first breath. In March 2024, ALMA mapped coj equals 2.1 at 230 GHz from BB at 16.6 AU, catching multiple narrow jets that changed over just 9 days kinematics, not rumour. That's the starting gun for the observing campaign, a hyper-volatile engine in deep cold, turning on years before perihelion. The question is, and will it wake? It's will we be looking, with the right instruments, often enough, to watch it change. So the window is not a single night. It's a phased plan that runs on discipline. Phase A, now 2027. Build the baseline. We need rotation, repeatability, and quiet flux. That means long, patient, light curves to bracket any periodicities. Multi-epoch CO maps to see if jet position angles repeat, rotation-locked vents, or drift seasonal illumination, fracture growth, and deep color, polarimetry, to capture the dust's handwriting before the inner system complicates it. BB's orbit gives us unusual phase angles off the ecliptic, exactly the geometries where coma physics is legible. If we spend 2 years dithering on cadence, well, spend the rest of the decade guessing. Phase B, 20, 27, 20, 30. Watch the season turn. As heliocentric distance falls from the high teens toward to 11 AU, CO should strengthen, CO2 may join, and the dust distribution should coarsen or fine in ways that betray layering versus plumbing. The literature on large distance activity is clear. Beyond the waterline, hypervolatiles drive the show, and they make comets do strange, slow things. If we miss the gentle bend in production rates now, we'll misread the steep parts later. Phase C, 2030, early 2031, inbound, lock the kinematics. The months before perihelion are when small, persistent thrusts integrate into measurable non-gravitational terms in the orbit fit. That's only interpretable if the gas and geometry were already tracked for years. The risk isn't that the orbit changes, it's that we see the change without the context and spend another decade arguing about models we didn't constrain when it was easy. Phase D, 2031-2033, outbound, read the echo. Because perihelion sits at 10.95 AU, the outbound arc is still cold enough for co-led activity to persist. That's our chance to test hysteresis. Do vents switch off symmetrically, or does the interior stay overpressured and lag the sunlight? If pits grow or roofs fail, morphology will change filaments, fans, and dust color slopes will write the post-turn diary. We only catch that if we schedule after the hype, too. Microhook, the sky itself is changing how we watch. The Rubin Observatory, LSST, will not only fatten the catalogue, it will de-bias how and when we notice things. Simulations show LSST would have found 40% of comets 5 years earlier, and at 2 times the distance compared with past surveys, and that it could at least double discovery rates of long-period, hyperbolic comets. For BB, Rubin's cadence won't discover it, but it will enforce regular, uniform looks that our patchwork schedules rarely deliver. That's what turns anecdotes into trends. What, specifically, are the deadlines? Rotation and jet geometry, 12-month currency. To separate rotation-locked vents from seasonal migration, we need clusters of CO maps and optical morphology at monthly to quarterly cadence, repeated over at least 2 full Earth years. Miss a year, and you confuse new vent with changed sunlight. The 9-day ALMA evolution proved the timescales can be short. Now we must ladder those short windows into a long spine. 2. Non-gravitational terms fit them while the lab is quiet. Because BB won't suffer close planetary kicks. Jupiter moid to 6 AU, tiny thrusts have a chance to stand alone in the orbital solution. But that purity only helps if we keep astrometry tight through the perihelion months. Let that cadence slip, and the fit will carry larger residuals you can't cleanly attribute to gas. The elements and their uncertainties will remember whether we showed up. 3. Dust physics before water speaks. There's a rare window before H2O becomes relevant, if it ever does, at 11 AU, where dust color slopes, phase angle dependencies, and polarization trace the layering just beneath the mantle. Wait until the coma thickens, and you'll be solving an underdetermined problem. Do it now, and you'll read the grain ledger while it's still legible. The long-distance activity literature spells this out. Hypervolatiles dominate 520 AU, and that is where we can diagnose the engine without the steam. 4. Outreach truth, on time. Perihelion beyond Saturn is a public-facing blessing, zero risk, maximum science. But public attention surges near dates, not footnotes. If we want telescope time granted and kept, proposal cycles should anchor to the 2031 perihelion, with staged deliverables in 2026, 2028, 2030 that prove momentum. Funding remembers calendars more than curves. What could still steal the window? Weather and scheduling, disguised as statistics. ALMA, VLT, large optical facilities, and radio arrays live on oversubscribed queues. A run of bad weather across a few awarded windows can erase a season. The answer is redundancy. Multiple facilities, overlapping modes, radio plus optical plus M, and pre-negotiated trigger protocols when CO jets spike, like traditional target of opportunity calls. The temptation to declare we know enough. We don't. The Hubble nucleus size tells us how big. The ALMA line tells us what's breathing. The orbit tells us how it moves. But none of that tells us how vents start and die, how layers fail, or how thrusts integrate across a full, cold perihelion. That knowledge lives in time series, not press releases, the timetable that sells itself. If we keep the next 6 years tight, we walk away with a rotation-resolved cojet atlas, a dust grain size evolution across unusual phase angles, a clean, non-gravitational acceleration record unspoiled by planetary kicks, and a population-level boost from Rubin that will tell us whether BB is a lonely cathedral or the first visible tower of a cluster we've been too biased to see. Underneath the urgency is a simple ethic. Publish the negative as loudly as the positive. If a season shows no jet migration, that's a constraint on seasonal forcing. If non-grav terms stay consistent with CO thrust models, that's a boundary on any phantom push. If Rubin's cadence shows no clustering once biases are purged, that's the end of a flirtation with patterns that were never there. Deadlines keep you humble. They also keep you honest. And then there is after. Perihelion doesn't end the story. It flips it. Outbound, we watch for hysteresis vents that lag the sun, pits that grow as roofs fail late, polarization that changes as mantles reseal. That arc is where models either predict or excuse. If we can keep the lights on, observing time, not spacecraft, we can walk BB to the door and know why it looks different when it leaves. The calendar won't bend. The date is the 23rd of January 2031. The distance is to 10.95 AU. The engine is co-bright already, and the surveys are about to regularize our glances. We are not early. We are timely if we move now. The difference between a documentary and a eulogy is whether we choose to be present before the turn, not just excited by it. The window is not kind, but it is fair. It gave us a head start in 2024. It gives us a metronome in Rubin, and it gives us a comet that breathes loudly enough to hear from here. It's waking up, and we're already late. The only answer is a schedule that admits no later. The algorithm doesn't know what it saw, just that it's real. Begin with the unease only machines can sharpen. We fed a decade of comet detections, positions, velocities, discovery conditions, limiting magnitudes into models that don't tell stories. They count distributions. The mandate was simple. Strip away what our telescopes prefer to see, then ask if the sky still prefers anything. That order matters. Long-period comets don't arrive at a metronome. The Milky Way's tidal field breathes them inward and outward, while passing stars jostle the Oort Cloud at irregular intervals. That background guarantees lulls and gusts. It does not guarantee the specific shapes human eyes think they recognize. The hard part is purging observational bias. Surveys lean northern. Schedules tilt with the seasons. The ecliptic is over-policed. Fast movers smear into streaks and drop below detection thresholds. That cocktail can manufacture fake clusters, so the first layer of code has to learn the survey before it learns the sky. Recreate the actual pointings, weather, seeing, depth, cadence, downtime, trailing losses, so the data entering the model is no longer a collage of holes. Only when the table is level do we let the algorithms hunt. Unsupervised methods, density clustering in original orbital energy, 1a, inbound direction on the celestial sphere, and discovery time are our opening move because they assume no shape. If, after debiasing, there's still excess density in some direction, epoch, or energy band, that's a statistical signal. Something is showing up more often than random. Theory says this can be real. A star grazing the Oort Cloud can seed a long, low-contrast shower that rides the galactic tide drizzle for thousands to millions of years. When machine learning rediscovers that, without being told, it isn't inventing a plot, it's listening to the galaxy breathe. The unease begins to hum when those debiest models still flag pockets, eras, and sky patches where new long-period comets bunch more than a flat model expects. The output is agnostic. It labels clusters with confidence, scores, and uncertainty. It doesn't tell you why. That humility is crucial, because explanation lives in physics, not in a loss function. Comet showers are expected. Gaia's catalogue now lists dozens of past and future stellar flybys within a parsec, with one heavyweight on approach that will torque the cloud in about 1 million years. The lag for any single body to fall inward is mere scale, so you can't name a culprit for BB. But the existence of dense seasons is hard to argue against. The model isn't seeing intention. It's probably seeing tides and stars with a local accent. Where does BB fit? Not as proof of a burst, but as a calibration lamp. A cathedral-scale nucleus breathing CO at 1617 AU gives us a meticulously measurable laboratory for cold activity, jet angles, line widths, rotation-locked vents right when we need it. Over the next decade, the Rubin Observatory will patrol the sky with uniform cadence and depth, inflating the denominator that machine learning requires. When that denominator grows under fair rules, the algorithm's verdict on clustering will either harden, physics, or fade, bias exposed. Without that denominator, AI is only clever with small numbers. We also tried to tempt the net. We hid synthetic planes of fake comets in the data, perfect alignments a human might hope to see if a distant shepherd were tugging strings. After debiasing, the model rejected the pretty straight lines, but kept a few fuzzy pockets that match Oort Cloud dynamics. Clusters smeared in time and direction, not immaculate geometries. The refusal is the point. Nature's real is messy, with memory and noise. Machine learning in small-body astronomy is more than clustering. Classifiers already quietly guard telescope time. They learn the shape of a coma, detect faint extendedness a human would miss, and rank candidates for follow-up. Convolutional nets localize faint fuzz. Tree ensembles prioritize targets. Anomaly detectors pull strange objects to the surface. That doesn't prove a population-level pattern in arrivals, but it disinfects the inputs before any statistical test. Clean in, honest out. Physics stays the adult in the room. A model isn't allowed to declare a pattern unless a forward model can reproduce it. We generate synthetic universes by evolving billions of test particles under the galactic tide and a realistic ledger of stellar flybys. Then march those particles through a survey simulator with real cadence, weather, and depth. If clustering reappears at the same strength and shape, we call it expected. If the real sky's clustering sits above that envelope, we have surplus that demands either an unmodeled bias or a new lever. That loop bars overinterpretation. The siren calls hidden planets. Shadow forces will always be audible, but sequence keeps us honest. First, ask whether known mechanisms can overshoot naive expectations. The tide isn't static. Local disk structure, spiral density waves, and primordial anisotropies in the Oort Cloud can all modulate the injection rate. Then consult Gaia's ledger. Many close passes still need to be folded in with proper uncertainties. Only after both steps fail do we test additional hypotheses. Even for the favorite invisible shepherd, the battleground remains distant. TNO architecture and biased samples, not Oort Cloud long-period arrivals like BB. The algorithm won't settle that debate. Better catalogues might. Hera's the useful, prickly place we've reached. After debiasing, arrivals are not perfectly flat in time or direction. They show low-contrast excesses that survive cross-validation, exactly what dynamics predicts when stellar encounters modulate the tidal baseline. The model flags them. Physics explains them. Gaia's encounter lists supply the scaffold. Dozens of stars inside 1 parsec, past and future. So showers exist is not a stretch. It's a forecast with names and error bars. Rubin, LSST, will provide the cadence that lets AI stop guessing at the denominator. If apparent clusters dissolve as the catalogue grows, they were artifacts. If they strengthen, the galaxy did it. Either outcome is a win. BB's role is calibration, not proof. A bright, slow, measurable comet that teaches the feature set for cold activity while the population picture comes into focus. One monument does not make a mob. It makes your models better. From here, the marching orders are written in code and on calendars. 1. Keep debiasing honest. Bake in real weather logs, nightly depth, and trailing losses so the comparison is sky versus sky, not sky versus fantasy. 2. Cross-match with Gaia as a routine, not a flourish. Every candidate cluster gets a look up against encounter epochs and strengths, with mere lags folded in. If a star can explain it, let it. 3. Publish negatives. When a flagged cluster evaporates under new data, say so. Absence is information. AI learns from true zeros. 4. Use BB as ground truth for cold activity features. CO spectra, jet geometry, rotation-locked vents, non-gravitational terms. So pattern finders trained on distant comets don't mistake chemistry for choreography. The algorithm doesn't know what it saw, just that it's real. The rest is on us. We decide whether real means a tide we finally resolved, a star we finally credited, or a surplus that asks for a new lever. We decide whether to treat BB as a headline or as a calibration lamp. We decide whether our unease becomes discipline surveys simulated before statistics, statistics checked against mechanism, mechanisms accepted when they are enough. If the pattern survives Rubin's light and Gaius ledger, the dread changes shape, not fear of intent, but respect for scale. The galaxy can bunch arrivals without speaking. The Oort Cloud can remember a shove for 1,000,000 years. BB can be singular and still belong to a chorus we were too biased to hear. Let the machine keep time. Let the physics give meaning. Then we'll know what kind of pattern we've actually found. What if it wasn't a planet, but a shadow? Start with the thing we can't point at. The Milky Way's halo is a sea of mass, with no light dark matter, whose only reliable verb is pull. Near the sun, that sea is thin, but everywhere, a background density of roughly a few tenths of a GeV per cubic centimeter. It doesn't blaze like a star, or sweep dust like a planet. It hangs, continuous, and adds a small, steady tug to everything that moves. If a shadow could steer a comet, this is the shadow we mean. But dark matter is not smooth marble. In the cold dark matter picture, it granulates. Subhalos the size of globular clusters, and smaller, should pepper the halo, most too dim to carry stars. We do not see these clumps directly, we infer them from scars. A long, cold stellar stream is a seismograph for gravity, and several show ripples and gaps that look like past punches from invisible mass. GD1, the stream that arcs across half the northern sky, wears a break and a spur that many teams modelled as the wake of a dense, starless perturber. If subhalos really haunt our neighbourhood, the galaxy is littered with silent knuckles. Would such knuckles push Oort Cloud comets like BB into the inner light? The honest sequence is physics first, romance second. We already know what loads the dice. The galaxy's own tidal field slowly torques the distant cloud and lowers perihelia. Passing stars spike the rate in long, sloppy showers that last far beyond the encounter itself. Those two mechanisms, tide plus stars, reproduce most of the statistics for long-period comet arrivals. They are the baseline that explains why anything falls in at all. If a new lever is needed, it must move the ledger beyond what tide plus stars predict. Dark matter's average pull near the sun is real but meek. That local density, the few tenths of a GeV per cubic centimeter, that experiments assume when they calibrate detectors, implies accelerations far smaller than the tides from the galaxy's visible disk, and far smaller than the impulses of even modest stellar flybys. That doesn't make DM irrelevant. It makes it background. To take the driver's seat in Oort Cloud dynamics, dark matter would have to clump nearby and cross our path closely, or WED have to be moving through a dense stream. Both are possible under LCDM, but neither follows by default. The null hypothesis remains tide, and stars did it. Now imagine the granular case, the subhalo, the stream, the shadow with edges. If a dark clump brushed the cloud, it could inject a statistical surplus, a gentle overpressure of new arrivals spread across millions of years, not a single file of comets marching in lockstep. In the sky, that surplus would look like a low-contrast season, not a spotlight. Our Part 13 machine saw hints of such seasons after careful debiasing. That doesn't prove a subhalo. It says, something beyond Poisson noise is there. Gaia's catalogue of real stellar encounters is the first suspect. Whatever is left over, if anything survives, Rubin's fair cadence begins to earn the word shadow. The burden of proof is high. Subhalos are a prediction, not yet a map. Bring BB back into the frame. Its cojets, at 1617 AU, are chemistry speaking in the cold. Its path, almost perpendicular to the planetary plane, is exactly the sort of geometry an isotropic Oort reservoir throws at us when tides and stars do their slow work. There is no need to invoke a dark stream to explain this object's arrival. That does not mean dark matter never matters. It means we cannot claim it here. The right sentence is the narrow one. BB's present behavior and orbit need no physics beyond tide plus stars. What then of phantom forces not matter, but modified gravity? In every decade, the solar system offers a rumour. In the 2000s, it was the Pioneer anomaly, a tiny sunward drift in tracking data that looked like new physics, until a full thermal recoil model of the spacecraft showed that waste heat from the RTGs and electronics pushed exactly as much as the Doppler said. The force dissolved back into engineering. More formal ideas, like MOND's external field effect, have been confronted with the cleanest ruler we have, Cassini's exquisitely precise radio tracking at Saturn. The result? No deviation from general relativity at a level that would give MOND easy room. Large chunks of parameter space are simply gone. Phantom forces are interesting. In the solar system, they are caged by data. Could a fifth force hide further out and only show up in comet orbits? Planetary ephemerides are harsh referees. Extra long-range pulls change perihelion precessions and secular terms in ways that high-precision fits would notice. And modern analyses use everything from Mercury to Saturn to asteroids to bound such effects. Recent work folds in OSIRIS-REx's tracking of Bennu and Apophis to push the limits tighter. If a new force is out there, it must be weak enough to dodge all those constraints and yet strong enough to steer a ragged iceberg in the dark. That combination is not impossible. It is unlikely. We should test it with comets, but we should expect the null. The more interesting dark matter angle is not a single shove, but a signature. Stellar streams remember punches for hundreds of millions of years. If dark clumps exist, they should pepper those streams with telltale gaps, spurs, and kinks. That is where the evidence is accumulating, not in one comet, but in long, cold ribbons of stars that have no other way to get scars. As this map of scars matures, we can ask a cleaner version of the BB question. Given a measured subhalo population around the Sun, what surplus in long-period comets should we expect over the next few million years? That is a forward problem. It will have a number. Until then, we have priors, not proof. So we draw the influence map outward without pretending certainty. The galaxy's tide is the floor. Stellar flybys are the weather. Dark matter is the air thin, everywhere, and sometimes knotted. Modified gravity is the alternative dictionary we keep on the shelf and consult only when the ordinary words fail. For BB, the ordinary words are enough. For the population, the verdict is pending until Rubin supplies the denominator and Gaius' ledger is fully mined. Our to-do list writes itself. Treat dark matter as background in BB's interpretation and as a hypothesis in the population study. If an excess survives tide plus stars in DB-ACE catalogues, test subhalo models next. Use stellar streams as calibrators for clumpiness. The more we trust the subhalo census from stream scars, the less we have to guess about any comet surplus. Keep solar system phantom force claims tied to rulers. Cassini-grade tracking, planetary precessions, and asteroid ephemerides have veto power. Do not outrun them. Publish the nothing. If Rubin flattens the apparent seasons, let the record show that the shadow was our bias all along. What if it wasn't a planet, but a shadow? It's a good question when our maps feel too clean. The answer, for now, is a partition. BB's arrival fits the tide and stars machine we already trust. Dark matter may write weather on top of that climate, but we have not caught it in the act. The shadow is there. Its hand on this traveller is not. Our whole solar system is tilted, and no one knows why. Hold the model in your hands the way a child holds a mobile. A bright sun at the centre, planets circling in a single, calm plane like beads on a wire. Now tilt the wire. Not much, just 6 degrees. The calm isn't broken. It's unsettled. That small lean is enough to haunt dynamics, textbooks, and whisper that something touched us long ago, or is still touching us now. We live in a slightly crooked machine, and we don't yet agree on the story that made it so. A tilt that small is easy to say, hard to ignore. The Sun's spin axis is not perpendicular to the average planetary plane. It leans by about the width of a finger held at arm's length. If you were building a clockwork from scratch, disk of gas collapsing, dust flattening, planets condensing, you'd expect the hands and the face to line up. They mostly do. Mostly is where the wonder gets in. 6 degrees is a memory. Of what? We're still deciding. There are gentle culprits. Over billions of years, planets trade talks with one another, the way dancers trade weight. And the whole system precesses axes slow wobble, planes slowly nod. In that view, the lean is a long note, not a jab. You can write equations that make the tilt look inevitable, a natural mode of the solar system's deep music, the way a bell prefers certain tones. But tidy mathematics can also tidy away the very itch that sent you looking. If it's just precision, why this much and not less? Why now and not earlier? Why does the clock choose this note and keep it? Then there are the bold culprits. Imagine a distant body, heavy and slow, a shepherd you haven't found yet, using a long lever to torque the whole planetary plane over eons. Or imagine an early jostle the Sun, spinning down through a magnetic wind while Jupiter still drifted, a tug of war that left a permanent slant. Turn the imagination dial further, and you reach the wide world beyond. The galaxy's tides rocking the far reservoir of comets, stellar flybys bending the outer architecture, the large-scale environment writing a tiny accent on the way our own system sits. BB steps onto this stage as a reminder, not a proof. Its orbit, a near right angle to the familiar planetary disk, doesn't mean the disk is wrong. It means the cloud that feeds BB is almost isotropic, a frost of orbits pointing everywhere, made that way by time and distance. But BB's path, slicing through our plane like a blade through gauze, is a physical metaphor for the anomaly. The universe does not respect our tidy drawing. Somewhere between the disk's memory and the cloud's freedom lives the angle we keep measuring. Jupiter, the archivist, carries clues in its gravity field. The way its mass bulges and balances encodes the story of a planet that likely migrated, that may still be exchanging momentum with the swarm of small bodies it shepherds and scatters. Each harmonic in its gravity map is a syllable from the early days, a reminder that the planetary system didn't freeze in place after it formed. Jupiter's slow trades with Saturn etch long-period cycles into everyone else's motion. If the solar system is a choir, Jupiter sings the loudest, and when the loudest voice leans, it can coax the song to lean with it. Further out, the star map wraps around us like a quiet sea. The Sun doesn't sit still. It swims through local currents, past associations, and loose streams along spiral structure. In that slow swim, the disk of comets, the Oort Cloud, feels more of the galaxy than the planets do. It's plausible that the tilt story has two acts, the inner family exchanging talks until they settle on a slightly cocked stance, and the outer family remembering every distant wave and passing neighbour in the posture of its arrivals. If that's true, the 6-degree lean is just the visible half of a larger misalignment written in much colder ink. None of this demands a villain. A few degrees can be the residue of many cooperative processes, the way a boat carries a list after winds from a dozen storms. What keeps the door open is that the list is measurable, persistent, and hard to pin on any single gust. That's why we keep checking it from different angles, tracking planetary spins with exquisite spacecraft radio, refining orbital planes with decades of astrometry, simulating ensembles of young disks under evolving magnetic winds, asking what torque the Sun's own mass loss could have banked, and testing how early migration might have turned a clean alignment into a permanent lean. BB doesn't answer those questions. It does something more valuable for a clock this big. It gives us a second hand to watch while we listen for the hour. Its near-perpendicular path guarantees unusual observing geometries, phase angles that the ecliptic rarely delivers, scattering regimes that turn dust into an honest narrator. As we measure BB's jets across seasons and its tiny non-gravitational nudges, we measure them from a frame tilted to our own. The data won't repair the 6 degrees, but it will tell us how the system behaves under that slant, how comets breathe when the sunlight strikes from odd directions, how dust writes under a geometry the inner planets seldom offer. Wonder has room for restraint. There's a temptation to bind the tilt, the cloud, the comets, and a hypothetical distant world into a single, glamorous story with one cause and many effects. The sky often chooses the other way. Many causes, one small effect. A little tilt from early disk-star coupling, a little more from planet-to-planet trades, a varnish of migration history, a slow bias from the Sun's loss of spin. Add them like transparencies until the 6 degrees appear. The answer that arrives may be less cinematic than we crave. It will also be truer, and yet the cinematic keeps trying. Picture the solar system as a lantern hung slightly askew in a dark room. The light still fills the room, but every shadow falls with a quiet bias. Comets approach along paths that do not care about our furniture. Planets keep time in a plane that isn't quite the tabletop we imagined. Spacecraft fly, measure, return numbers that agree to too many decimal places for comfort, and the decimals still insist. The lantern tilts. What we can do next is precise, not grand. We can refine the angle again, tie the Sun's spin axis to distant quasars through careful reference frames. We can keep mapping Jupiter's field as if it were a relief map of history, trace Saturn's wobble, read the small, steady tides in asteroid families, the way a geologist reads a mountain range in wrinkles of rock. We can watch BB long enough to make its off-plane geometry a gift rather than a curiosity. We can check whether future Oort emissaries favor any slant at all when viewed against the ecliptic, or whether their reign is as directionless as legend says. The 6 degrees do not threaten us. They instruct us. They say the neat illustration you saw in school was a kindness, not a contract. They suggest that even in a system built by collapsing into a single plane, history has fingers, and those fingers leave angles. They suggest that architecture isn't perfection, it's preference plus memory. Our whole solar system is tilted, and no one knows why. For now, that line stands. It stands with humility, not with drama. It stands beside BB's blade-thin crossing of our plane, beside the slow humour of Jupiter's long song, beside the star map that wraps our neighbourhood and the quiet drifts of the Sunday. The tilt is small enough to be a whisper, large enough to be a thesis. We will likely solve it with accumulation, not revelation. A few better gravity fields, a few longer baselines, a few more off-plane comets traced through seasons, until the sum of small certainties outweighs the appetite for a single cause. When you tip your head at night, the sky still looks level. But the level is an agreement, not a truth. The truth is an angle modest, patient, unashamed to be less than perfect. In that angle lives the system we actually inhabit and the work we actually do, to measure, to listen, to let the crooked be informative. The emptiest part of the universe may be touching us. Begin not with an object, but with an absence. Picture a volume of space so underfilled that matter is more rumour than substance, galaxies thinned to a few shy lanterns, gas stretched until it forgets its own name. We call such regions supervoids. They are not holes punched through the cosmos. They are the places where structure never properly gathered, where gravity wrote a sentence and omitted the nouns. If clusters and filaments are the universe's handwriting, a supervoid is the breath between words. What could breath do? On human scales, nothing. On galactic scales, a little. On cosmological scales, enough to be measurable. Light leaving the early universe trails its hand across every hill and hollow in the cosmic web. Where space is denser, photons climb in and out of deeper wells. Where space is emptier, they coast through shallows. If those hollows grow while the light passes, the photons give up a whisper of energy they never get back. We catch that whisper as a temperature bruise on the oldest light. We can see the cosmic microwave background, CMB. It's called the integrated Sachs-Wolf effect, a photon's faint receipt for the evolving landscape it crossed. Some bruises are ordinary, low contrast, politely random. One, infamously, is not. On the CMB sky, there is a dim patch colloquially called the cold spot, a chill a few degrees across where microwave photons arrive just a little less energetic than their neighbours. It might be a statistical fluke in a universe large enough to permit such coincidences, or it might be the fingerprint of a truly giant underdensity, a supervoid big enough, coherent enough, to drain those photons more than our tidy models expected. The debate refuses finality, which is another way of saying the sky still gets to surprise us. You don't need a supervoid to talk about BB. Long-period comets arise because the Milky Way's own tide leaks angular momentum from the Oort Cloud, and passing stars tilt the reservoir's orbits toward the inner light. That machinery fits neatly into textbooks without mentioning the word void. And yet the notion that grand, low-density regions can nudge the local tide is not idle poetry. Galaxies sit inside a foam of structure, filaments feeding clusters, sheets connecting filaments, voids bulging between. A galaxy's halo does not float in isolation. It swims in a current you can't see, and that current sets the background against which every outer reservoir evolves. Hold that current in mind when you place the Sunday. Our system orbits within a spiral arm in the Milky Way, itself woven into filaments and surrounded by underdensities at larger scales. If you pan out far enough, the map of near to mid-cosmic structure becomes a patchwork of emptinesses and gatherings. Regions like the local void, underfilled compared with their neighbours, walls like the local sheet, binding flows, larger attractors and repellers that shape the motion of whole associations of galaxies. These are not the Emperor's new clothes. They are the slow winds that, over hundreds of millions of years, decide how long a far-flung comet lives undisturbed before its perihelion ebbs inward. You can think of it this way. The tide that stirs the Oort Cloud is set by the Milky Way's disk plus the mass just beyond it. Change that exterior balance by a little tug from a wall, slack from a neighboring void, and you change the amplitude and phasing of the tide by a little. A little measured against a comet's million-year nap is not small. You don't need a void to aim BB. You need only accept that the base note under every long-period orbit is played by the galaxy's total environment, and that environment is lumpy on scales, so large the word landscape hardly qualifies. This is where awe pays rent. BB's orbit nearly perpendicular to the ecliptic. An emissary from an almost isotropic cloud looks local, a one-object story written by fractures and ices and jets. But the existence of that cloud, its replenishment, the cadence with which first-timers fall, those are not local at all. They are statistics produced by a galaxy in a cosmic web, modulated by passages through regions more and less generous with gravity. If a supervoid sits in the right place relative to our halo, it does not point a finger. It loosens a grip. Over giga-years, loosened grips become orbits you can measure. The CMB cold spot is the loudest invitation to make that connection, and it is also the loudest warning not to overreach. If a gargantuan void along that line of sight deepened while ancient light crossed it, the photons would arrive tired. They do. Whether the void is gargantuan enough, coherent enough, and alone enough to explain the entire chill remains unsettled. The lesson travels, though. The emptiest places we know can change what arrives at our detectors, and not just for light. Gravity does not ask whether its source has stars. Now return to the quiet practicality of a single comet. How does a thought about supervoids change the way we watch BB? Not at the level of scheduling telescopes, tuning receivers, or fitting non-gravitational terms, but at the level of interpretation. It lets us place BB's story inside a deeper frame. When we measure the rate at which the Oort Cloud resupplies the inner sky, we're not just reading the health of a reservoir, we're sampling the long average of the galactic tide, as written by our local piece of the web. When we look for clustering in arrivals over tens of millions of years, some part of what we are hearing may be the cadence of underdensities and walls our halo has wandered past. When we find nothing but the baseline, that nothing is a statement about how gently our neighborhood flows. There is something almost devout about giving emptiness a job. We have trained ourselves to prize the luminous and count the massive. Here we are, reminded that the quietest regions are not inert that a lack can act. The void doesn't reach in and flip a comet. It subtracts just enough gravity that the tide's hand feels lighter, and what was once a barely bound long ellipse can, given time and a few stellar nudges, become an invitation inward. A whisper added to a whisper until the room registers a draft. Caution remains the faithful companion of wonder. It is easy to turn the cold spot into an omen, the local void into a protagonist, the phrase Sax Wolf into a spell. We keep our feet by repeating the narrow truths. BB's orbit and activity are fully explained by the standard galaxy plus stars machinery. The link to supervoids is not a cause for this object, but a context for the population. Large-scale structure may set the long envelope of tides. Local encounters write the notes. Individual comets sing the syllables. The song we hear is the overlap, so let the largest structures in the universe into the room, but give them the right chair. They are the frame, not the brush. They are the tempo, not the hook. If a gigantic hollowness out there has cooled the ancient light by a few parts in 100,000, imagine what patience it has for rearranging the gentlest gradients of gravity here. Imagine how many BBs the universe has ushered inward without our notice, over eras when our species did not even have a name. Imagine, then return to the telescope and write a schedule. Awe is a good teacher. It is a terrible excuse. The emptiest part of the universe may be touching us. Not with a shove, but with a shrug that takes 1,000,000 years to finish. BB does not need that shrug to glow at 16 or 17 AU. We have the chemistry for that. It does not need that shrug to cut through our plane. We have the cloud for that. But when we widen the shot, we see the long company it keeps. Voids and walls and rivers of galaxies, all conspiring not to aim a single traveler, but to set the background against which travel makes sense. In that sense, yes, the emptiest places brush our lives. We are measuring inside their long weather. What if gravity isn't the only thing we got wrong? Start with the word we rarely question. Inertia, the stubbornness of matter, its refusal to change speed or direction without a reason. In every homework problem and mission plan, inertia is the furniture of reality. Mass sits there, while forces negotiate outcomes on its surface. We measure, we trust, we move on, yet sometimes the furniture creaks. Not loudly enough to rewrite textbooks in one night, but loudly enough that careful people tilt their heads. The modern creak has a history. 2 spacecraft, Pioneer 10 and 11, crept into the deep in the 1,970 seconds and kept whispering their positions by Doppler tone. Decades later, analysts noticed a tiny, sunward drift in those signals, a persistent acceleration so small it would take years to matter, but steady enough to deserve a name. The Pioneer anomaly became a Rorschach test: thermal recoil from warm electronics, asymmetric radiation pressure from power sources, unmodeled gas leaks, or a hint that inertia or gravity behaves just differently enough in the cold, quiet dark to leave a thumbprint. We did what science is supposed to do, kept our romance in one pocket and pulled out a ruler with the other. After a long audit of heat sources, geometry, and surface emissivities, a prosaic solution won by accumulation. The spacecraft themselves, bleeding heat unevenly, were ever so gently photon-thrusting backwards. The anomaly shrank into engineering. If there was poetry in the numbers, it lay in the patience it took to let warmth push a machine for years until the Doppler agreed. The thrill of new physics dissolved into the comfort of old thermodynamics. Still, one settled case doesn't seal the universe. Other small puzzles sit in the logbook flyby anomalies, tiny mismatches between predicted and measured speeds as spacecraft whip past Earth. Ephemeris niggles that yield to better tracking, but occasionally leave a scuff mark. The temptation to wonder whether what we call inertia is really a constant or a contract that frays in unfamiliar regimes. Most of those scuffs fade with sharper models, tighter reference frames, improved atmosphere and tide corrections, or simply with more data. But the question they suggest is not foolish. What would it look like if inertia itself bent a little? One family of ideas steps sideways from gravity entirely and asks whether inertia emerges from the information the universe can provide about motion. In these sketches, a mass reluctance to accelerate is tied, however loosely, to the horizon that bounds what it can know, to the way fields and vacuum structure respond when you push on the world. The details vary, and the names shift with fashion, but the intuition is constant. Perhaps inertia is not an intrinsic stamp so much as a dialogue with the rest of the cosmos, a response that could, under certain conditions, change its accent. It's a risky intuition you can paper over many mismatches by letting a constant slide, but risk alone doesn't make it wrong. Another, more famous path keeps gravity in the frame and modifies how it works when accelerations are tiny. Down here, apples fall and planets precess under Einstein's guidance. Far out, where the tug is whisper-soft, maybe the rules curve a bit. Such proposals have long been motivated by galaxy rotation curves and the fierce bookkeeping we do with dark matter. They are not aimed at comets or spacecraft, and the solar system is a hostile laboratory for them. Radio tracking at Saturn-level precision, lunar laser ranging, Mercury's perihelion, asteroid families, and spacecraft navigation all fence off parameter space until very little pasture remains. When the rulers are this good, new laws must be almost old in practice, indistinguishable from general relativity, where we can actually measure. Where does a comet like BB meet this conversation? At first glance, nowhere. Its faint, persistent, non-gravitational accelerations, the little pushes that tweak its orbit over months and years, have a working, testable cause: outgassing. BB is breathing CO in the cold, throwing out narrow jets that act as gentle thrusters. Change the vent geometry with rotation and season, and the push changes shape. Integrate those changes long enough, and the orbit remembers them. We have spectra for the gas and images for the dust. We can, within uncertainty, match the thrust to the chemistry. There is no need to soften inertia when you can count molecules, and yet the intellectual tension remains useful. Variable inertia dreamers would point out that deep space is the place to look. Long baselines, small accelerations, clean environments where noise integrates into signal. If an object's resistance to acceleration depended, however slightly, on its relation to horizons or on the information the vacuum can supply, you would expect the effect to be quietest, where grad students can't find it in a semester, and loudest, where missions last decades. That still doesn't make comets the right meter stick. They are active, porous, layered, and literally alive with fluid physics. The universe seldom hands you a clean experiment when a messy one will do. Even so, the discipline variable inertia demanded is healthy. It forces us to separate every contributor to a trajectory. Solar radiation pressure on dust, thermal re-radiation from asymmetric surfaces, gas jets tied to rotation, gravity from planets and the galaxy, pressure from the solar wind, relativistic corrections that vanish not because we don't include them, but because the numbers are too kind. When you run that gauntlet and nothing is left over, you earn the right to say there is no anomaly here. When something survives, you don't get to christen it new physics. You get to enlarge the checklist and ask nastier questions about the old. The larger cracks, if they exist, won't open under a single traveller. They will open in ensembles and in comparisons, identical spacecraft with opposite spins, flybys designed to be mirror images, comets watched across entire orbits with gas budgets closed by independent measurements, populations, not celebrities. They will open when two honest models disagree in a way that survives 3 generations of graduate students. They will open, if they open, at the place where the quietest assumptions live, units we never thought to convert, constants we never thought to question, symmetries we never thought to test because the last 100 tests were boring. There is also the human crack to mind, our appetite for a grand twist. What if gravity isn't the only thing we got wrong? Tastes good in the mouth, and stories made of wonder deserve flavour. But BB teaches a counter-aesthetic worth keeping. Its strangeness, the monument-scale nucleus, the early CO breath, the right-angle orbit isn't asking for a new metaphysics. It's asking for a schedule, for years of honest photometry and line maps, and orbit fits that leave no place for wishful thinking to sit. Or, here, is the patience to let the numbers be dull until the one that isn't has nowhere to hide. If inertia ever breaks the rules, the evidence will not arrive as a single plot at a press conference. It will arrive as a box of negatives. Spacecraft whose thermal maps leave no recoil to spend. Flybys whose atmospheres and tides are modelled to boredom. Comets whose thrust matches their spectra to within error bars so tight that the leftover push, if any, is an embarrassment to chemistry. It will arrive as a suite of independent rulers that point to the same sliver of difference from opposite sides. Until then, we keep the strange idea on a short leash and let foundational physics be hard to insult. BB's orbit carries the memory of tides and passing stars. Its present drift carries the breath of CO. Its light carries the signatures of dust writing under odd phase angles. The furniture holds. The creak we hear is the ordinary kind, the one a patient house makes as it settles in weather and years. That is not a consolation prize. It is a kind of grace. What if gravity isn't the only thing we got wrong? It's the right question to tape to a lab door, not the right answer to tuck into a paper. If the world bends there, it will bend where the math and the metronomes already are in the quiet, where our best instruments spend their lives listening. Until then, we give the old words their due. Mass resists, forces persuade, and comets breathe. The mystery is safe either way. It does not evaporate if inertia stays put. It waits for the next measurement we don't yet know how to take. Every orbit leaves a fingerprint. This one has a signature, not a confession, not a return address. A signature, the sum of forces that acted, memories they left, and the paths those memories carved. You can read it the way a geologist reads a cliff face or a physician reads a heartbeat. Layers, rhythms, excursions, returns. BB's signature begins well outside the light where we keep time, in a freezer-scattered halo of orbits so long and faint that the idea of now barely applies. Out there, gravity speaks in syllables of millions of years. Out there, scent is not a decision. It's a result. Start with the patient senders, the galaxy itself and the stars that pass through its rooms. The Milky Way's tide is the bass note, pulling on the Oort Cloud until far aphelia loosen and perihelia creep inward. Passing stars add syncopation, jolts that don't feel like jolts because you need a million years to finish hearing the word. Something sent it already has. One honest answer. The tide did. The stars did. They didn't point. They breathed, and the reservoir exhaled. Now add the nearer weather, the way the solar system carries its own crookedness. The planets exchange talks and precess. Jupiter conducts. The whole machine lists by 6 degrees from textbook neatness. We live in a slightly tilted lantern, and that tilt writes preferences into long timescales so softly you mistake them for fate. If you're looking for a signature on BB's envelope, a small part of the ink is that lean, not cause, but accent. Further in, the letters thicken. BB is active in the cold CO breath at 1617 AU, so the nucleus is layered and leaky, a body that keeps pressure where light can't reach and chooses its own seams. The jets are not random. They lock to fractures and rotation. Each vent is a stroke of handwriting in the dust, and each microthrust is a tiny clause in the orbital grammar. When we fit a non-gravitational term and watch it grow through seasons, we are hearing the interior edit its own path. The signature here is chemistry, choosing geometry, choosing dynamics. We try on bold ascenders because wonder asks for them. A distant planet putting an invisible thumb on the scale, a dark clump brushing the cloud, a fifth force that shows its face only in the quiet. None of those are crimes to consider. They are hypotheses with chores. Planet 9 lives, if it lives, in the realm of Kuiper architects, not Oort dispatchers. It would nudge statistics, not stamp an itinerary for BB. Dark matter is air-thin, everywhere, sometimes knotted, but the background pull near the sun is too meek to script a single traveller. At best, it tilts the long average. Phantom forces trip on the rulers we trust most ephemerides, radio ranging, laser ranging, and must be smaller than their own romance. Each could, in principle, add a flourish to the signature. None is needed for the main line. Then the map widens past comfort. Supervoids and walls, the cosmic weather at scales that turn galaxies into dust, shift the deep tide that the cloud feels. Not as a command, as a climate. You won't prove a void with one comet. You might hear its patience in a population. If Rubin shows seasons in long-period arrivals that survive bias and match the pace of known encounters, the signature becomes a chorus. The galaxy, the neighborhood, the cloud, all humming the same vowel for a very long time. Chaos sits in the margins, not as noise, but as a policy. In long problems, tiny differences in phase write different biographies. A fracture opens a month earlier. A jet precesses a degree faster. A star's path is a whisper closer than the median. Determinism doesn't die. It just stops being practical. What sent BB is a chain of lawful nudges whose details we cannot rewind without erasing ourselves to make room for more decimals. Chaos is not a shrug, it's a memo. Explain with envelopes, not with alibis. The machine age adds a new sense to the signature. We asked algorithms to remove our own eyesight from the story, to level the playing field of surveys, and to test whether arrivals prefer anything once bias goes quiet. They answered with pockets, not planes. That is a kind of authorship. The pattern isn't clean enough to claim orchestration. It's strong enough to keep catalogues honest. AI can't tell us who sent anything. It can score how weird now is against a million synthetic universes. When that score says low, but not impossible, the right emotion is not conspiracy. It's attention. On the ground, scent becomes a budget line. We can see it, but we probably won't touch it. The geometry is wrong, the calendar is rude, the watts go thin at 11 AU, so we trade hands-on for long looks. We take the signature apart with spectra and light curves and polarization, and we put it back together with orbit fits that remember gas more than rumor. A spacecraft would have been a beautiful instrument in a loud room. The sky can still be a quiet one. Is there a path where scent means intention? There is always a path, and stories deserve their corners. If you wanted to cross a system unannounced, you could wrap a machine in ice and let sunlight fake the engine. If you wanted to whisper, you would breathe in CO where water sleeps and leave no carrier where astronomers love to listen. If you wanted to look like BB, you would look like BB. The trouble with that path is its price. Every additional assumption has to camouflage itself against the details we already resolved: charcoal albedo, layered porosity, evolving jets, lack of narrowband transmitters, lack of specular glints. A perfect disguise is indistinguishable from the thing it imitates. Science has to prefer the thing. So, the synthesis is smaller than the headline and larger than any one cause. BB is an effect of systems we've only partly mapped. A reservoir built by early scattering, a galaxy that breathes on that reservoir, a drift through a lumpy cosmic web, occasional stellar grazes that turn drip into drizzle, a tilted clockwork near the sun that gives the drip a frame, a nucleus whose plumbing writes thrust in cursive, and a calendar that finds us attentive for once. Add those lines, and the signature that remains is not a name, it's a style. There's mercy in that verdict. If the signature is in style, we can learn to read it better. We can watch the rotation-locked jets through an entire cold perihelion and find out whether vents migrate like weather or break like bones. We can measure tiny accelerations in a clean, dynamical neighborhood and tie them to spectra we trust. We can let Rubin decide whether this decade is a gust or our eyes, and let Gaius' ledger of flybys apportion credit to real stars with real uncertainties. We can, in short, replace the question who sent it with how did this happen here, now, like this? Every orbit leaves a fingerprint. This one has a signature we can trace: tide, star, tilt, chemistry, chance. If there is a flourish we haven't learned the alphabet for, it will survive our better schedules. It will sit there after the gas is accounted for and the bias has been flattened and the catalogue has grown tiresome. It will invite the next part of the story, maybe a new lever, maybe a subtler map without making us ashamed of what the old one could already explain. For now, something sent it is true in the quiet sense that the universe is always sending. BB is not an exception to that generosity. It is one of the clearer sentences we've been given in a long time. We can honour it by reading carefully, by letting the room stay silent while the letters sort themselves, by resisting the urge to name a writer when the handwriting already tells us the instrument. The light is faint, the memory is long, the breath is cold. Add them together and you get the signature in front of us. Once it passes, it won't return for millions of years. There's a kind of reverence that only a long goodbye can teach. BB isn't a visitor in any human sense. It's a sentence the galaxy started writing before our species learned the word for sky. In 2031, it will pause at a cold perihelion, still beyond Saturn, turn its long ellipse by a fraction of a degree, and continue a journey no calendar will ever finish. For us, the turn is the only chapter we get to read in real time. The question is whether we read it with enough care that the next century can still learn from our notes. We can still learn the shape of its breath. Outgassing at 16, 15, 12 astronomical units is not supposed to be interesting. BB made it interesting by letting carbon monoxide do the work while water sleeps. The jets tell a story in narrow strokes, position angles, line widths, how their brightness pulses with rotation, how they migrate or refuse to through seasons. If we stitch radio maps and high-resolution optical images into a single atlas, locked to a rotation solution we trust, we'll know whether the engines are rooted in ancient fractures or in new failures of a layered crust. We'll know whether vents wake, wander, and die like weather, or break like bones and stay broken. We can still learn the grammar of its motion. The non-gravitational term in the orbit fit the tiny, persistent acceleration that chemistry writes into dynamics will keep growing as the comet brightens toward its distant turn. Those numbers are not footnotes, they're a ledger. If the fit we carry through perihelion matches the thrust predicted from gas production and vent geometry, well, close a rare loop, composition jets force orbit. That loop is the antidote to rumour. It's how you leave the next generation a standard, not an argument. We can still learn what its darkness hides. Polarimetry and colour, done patiently across a range of phase angles the ecliptic rarely grants, will pin down dust-sized distributions and the degree of layering just under the crust. Thermal measurements, broadband and line, can trap thermal inertia, the telltale of how quickly the nucleus conducts and stores heat. Together, those become a portrait of a body that remembers cold differently than the comets we meet near the Sunday. If the portrait feels familiar, terraces, pits, mantles, then Rosetta's geology scales cleanly to cathedral size. If it doesn't, BB will have widened the taxonomy by being a counterexample we actually measured. We can still anchor the population with one honest monument. A nucleus roughly 137 kilometers wide is a bulwark against speculation. Its mass, albedo, and porosity set limits on what comets can be and still be comets. In models of the early solar system, BB becomes a boundary condition. Future papers that juggle migration and scattering and the birth of the Oort Cloud will have to fit this stone into their mosaics. Every extra night of photometry and every clean spectrum raises the cost of hand-waving for decades to come. We can still make the outbound arc count. After perihelion, the light won't switch off. It will dim like a room at dusk. Hysteresis, the lag between sunlight and breath, lives there. Do vents close symmetrically? Do roofs fail late, as internal pressure works on old seams? Do dust slopes redden or blue as mantles reseal? The answers are not dramatic in the way headlines like, and that's exactly why they matter. They become parameters that make or break models in the silence, after the news cycle moves on. We can still hold the door open for the public, not as a spectacle, but as belonging. Perihelion, at to 11 AU, carries zero risk to Earth and maximum permission to be curious. That's an invitation to build a ritual around careful attention. A shared calendar of observation windows, public dashboards that visualize jets in near real time, classroom kits that let students fit a light curve and watch the rotation solution snap into place. If we do this well, the memory of BB will not just live in papers, it will live in a generation that saw patience rewarded by meaning. We can still decide what we are willing to miss. Oversubscribed telescopes will not bend for poetry, they bend for preparation. Proposals that treat 2031 as a single night will lose to proposals that treat 2026, 2028, and 2030 as scaffolding. Radio time that waits on triggers when a jet brightens, optical time that agrees to repeat the same geometry 3 months apart, polarization that returns to the same phase angles by design. These are the habits that turn isolated snapshots into a coherent film. The comet is giving us time. The only way to squander it is to treat each night like an event instead of a sentence in a paragraph. We can still build the ledger that lifts the population debate above taste. AI has already told us how easily bias forges patterns and how stubborn a few pockets remain after you strip bias away. Rubin will give us cadence. Gaia will keep adding names and error bars to the list of passing stars. BB can be the calibration lamp for that whole effort, a ground truth case where the non-gravitational term and the gas budget are both known to within honest error. When future algorithms ask whether a season of long-period arrivals is physics or optics, BB can be the footnote that says, "We checked on a comet that gave us room to check." We can still make generosity part of the method. Release the negatives, the nights when nothing much happened, the maps where jets didn't move, the fits that refused our favorite slope. Publish cadence plans so other facilities can braid theirs through ours. Archive the raw. Comets forgive ego badly. They reward stubborn, transparent work. Before it's gone, should feel less like a countdown than a covenant. We owe the sky our best habits, while it gives us a case we will not soon see again. We can still accept the limits and name them out loud. We probably won't touch it with a spacecraft. The geometry is unkind, and the watts are thin this far from the Sunday. That doesn't make the endeavour smaller, it makes it cleaner. The sky is enough when the target is this large, this dark, this patient. A mission would have turned the volume up on a few instruments. A disciplined, multi-year campaign can still hear the whole song. Mostly, though, we can still give it our attention without pretending. Attention is control. BB will not notice we are watching. It will not lean toward our lenses or reward our schedules with theatrics. It will do what cold does under weak light. Breathe where it can. Remember where it must. Carry on. Our reverence lies in the willingness to match that steadiness with our own, to keep the calendar we set, to show up when the weather lets us, to write down what we see when seeing feels routine. When it leaves, it will leave a better field behind. Models tightened by stubborn data, students who learned patience from a slow object, a public that saw a story without danger and chose to care anyway. And somewhere, a paper's dull middle section where a small number matches another small number to within a narrow bar, and the author lets the figure speak without a flourish. Those are the kinds of victories that last. They are the kind that survive the fashions of a decade and keep being useful when our names have been forgotten. Once it passes, it won't return for millions of years. The sentence is not a threat. It's a measure of how big the room is and how briefly our lamp is on. The right response is not to rush. It is to work with a clean hand and a full breath while the lights are bright enough to see by. BB will write the next half of its sentence in the dark. We still have time to finish our paragraph. Sometimes the answer isn't what it is, but what it makes us feel. There is a way an ordinary evening can become a cathedral if you step outside and breathe. The sky does not move any faster for your attention. The stars do not lean in to be generous. And yet, for a moment, attention rewrites the scale of your life. You are smaller in a good way. You remember the exact weight of air in your lungs. You notice the hush between sounds. The world did not change in that minute. You did. BB is that kind of minute. It did not give us aliens. It didn't even try. It did not force gravity to confess a secret code or bend the rulers we've trusted across the decades. The old machinery held. Tides and stars, chemistry and geometry, patience and error bars. We argued, because arguing is how we breathe in science. But most of what mattered survived the argument with its dignity intact. The nucleus stayed dark. The jets obeyed their physics. The orbit remembered the thrusts we could count. In the ledger where revolutions go, the page is clean, and yet try to tell the story as if nothing happened. A monument of ice woke in the cold and wrote its breath across our detectors for years. Our best instruments learned how to be quiet long enough to hear it. Our models earned small victories that will outlive our names. Students learned to keep a schedule. A public that didn't owe us attention chose to give it anyway. We sharpened the tools that will read the next visitor more clearly, because this one took the trouble to come by at a speed we could follow, at a distance that kept us honest. In the ledger where meaning goes, the page is full. Meaning is tricky like that. It does not require a twist. It requires a posture. Wonder is not the same as gullibility, and humility is not the same as retreat. What BB asked from us was uncomplicated. Show up, measure, publish the boring parts, speak plainly when you don't know. Do that long enough, and even a negative becomes a door. No narrowband signal is not a disappointment. It is a contour on the map of what comets are. Jets consistent with CO is not a shrug. It is a sentence you can build the next paragraph on. We think of discovery as fireworks. Often it is daylight visible, steady, hard to dramatize, impossible to live without. If nothing else, BB reminded us how large silence can be. A comet does not narrate. It exhales. It turns the sunlight it is given into a thin script of gas and dust, and it lets our optics do the rest. We learned to read that script more fluently. We learned which kinds of quieter information and which are simply noise. There is a moral comfort in that, the same one you feel when an old clock chimes on time, not surprise, but trust. The universe is allowed to be trustworthy. That does not make it dull. We also learned that human scale is malleable. A 6-year campaign sounds like forever, until you realize it will be 2 or 3 notes in a career. A 1,000,000-year return sounds like eternity, until you realize it is only one heartbeat for the cloud that sent BB in the first place. We found our place between those 2 clocks and discovered it was livable. There is a gentleness in planning something you will never see completed and doing it well anyway. There is a kind of courage there, too. What changed? If not the laws, the way we hold them. We will go into the next decade of sky with an appetite shaped by this object. More careful about bias, more rigorous about cadence, more transparent about failure, kinder to the part of ourselves that loves a good story but insists on footnotes. We will carry a better intuition for cold activity into every model, and we will stop pretending that far means quiet. We will remember that a plane change can be impossible and the science still be generous. We will stop mistaking drama for value, and in a narrower, more tender way, BB changed the room we worked in together. There were nights of nothing, there were runs of weather, instrument alarms, proposals declined, and lines that didn't quite emerge from the noise. There were also small triumphs, a cross-check that matched, a jet that kept its angle, a fit that settled where we thought it would. Those are not plot points, they are craft. Craft is how meaning becomes durable. Craft is how wonder earns the right to stay when the headlines move on. Perhaps the most honest sentence we can write about BB is this. It taught us to pay attention without a reward structure. The comet didn't care whether we watched. The sky wasn't keeping score. We watched anyway, and we kept score anyway, because attention is how we practice belonging to a universe that did not need to invite us, but did not lock the door. That is the kind of lesson that spills past science into something more human. Patience as a form of love, precision as a form of respect, silence as a form of fellowship. Sometimes the answer isn't what it is, but what it makes us feel. What does it make us feel? Small, yes, at last in the right direction. Also capable, also grateful. Also connected in the honest sense, not that everything happens for us, but that everything happening around us is within reach if we show up and do the work. It is easy to confuse transcendence with spectacle. BB's transcendence was the opposite. A long, low note that never broke, and a community that learned how to hear it together. When BB fades, the sky will look the same as it did before. We will still be on a small planet with errands and noise. The sun will still lean by its modest 6 degrees. Jupiter will still hum the loudest part in the choir. The galaxy will still breathe on a reservoir too large to name out loud. None of that will have changed because of us. But inside the small reach where our hands and calendars live, we will have become the kind of people who can carry a quiet object across several winters and tell the truth about what we saw. That is not a revolution. It is a competence. Competence is a form of hope. There is a last image worth keeping, a narrow line on a spectrum, pulled from wide noise by time and care. A light curve that looks like nothing until you overlay last month's and notice how faithfully the peaks line up. An orbit fit that tightens so gently you only see the progress if you annotate your own annotations. Those are not special effects. They are the way reality reveals itself to those who refuse to hurry it. BB did not owe us a revelation. It gave us practice. It changed nothing. And everything. The laws remained, the frames held, the numbers lined up. But the person holding the printout, the team building, the cadence, the audience that let a slow story bloom, walked away different, less certain that drama is truth, more certain that truth, when you tend it, becomes beautiful on its own. If you want a benediction, take this. Let the next object find us, as we tried to be for this one present, generous, unafraid to say we don't know, untempted by flourishes that the data cannot support, unashamed to let wonder be quiet. The sky will not clap. That's all right. Clapping is for rooms. We will know we did it right when the silence after a measurement feels like a held breath rather than an empty one. Sometimes the answer isn't what it is, but what it makes us feel. This one left us steadier, kinder to our instruments and to each other, and in love with a world that stays immense no matter how well we learn to measure it. That is enough to carry forward.